Every expert in cometary science across the globe is in unanimous agreement. The behavior of the interstellar visitor known as 3IATLAS defies all previous understanding. As this enigmatic object hurtles toward its anticipated encounter with Mars in October, it exhibits phenomena that seem almost otherworldly. Its atmosphere is expanding rapidly, glowing with a vibrant green hue that stretches far beyond the size of Jupiter's diameter, creating an immense luminous shroud that continues to grow. Its brightness fluctuates unpredictably as if guided by some unseen hand, and its tail manifests in ways that challenge the fundamental laws of solar physics. The dust particles scattering light from this comet produce optical effects never before documented or measured, revealing complexities that surpass our current models. As it draws nearer to the red planet, the object appears increasingly crafted rather than naturally occurring, a deliberate design rather than a chance celestial formation. Yet amid these astonishing observations, the most astonishing part of all remains unspoken: a profound silence from the world's leading space agencies. While amateur astronomers worldwide post tentative images on social media, capturing glimpses of what appears to be an anomaly from the cosmos, every major space telescope, Hubble, James Webb, Gemini, has fallen unexpectedly silent since August. This silence is not merely a pause, it is a mysterious void that invites suspicion and curiosity. So stay with me as we delve into the depths of this phenomenon, exploring why 3IATLAS is behaving in such bizarre and inexplicable ways, and most crucially, why the authorities and scientific institutions have chosen to go quiet at what could be one of the most significant celestial events of the 21st century. Part 1. A comet that refuses to follow the rules. In the middle of September of the year 2025, an event occurred that defied all predictions. 3IATLAS, the interstellar visitor, suddenly exhibited a rapid brightening, far faster than any model or expectation had forecasted. This unexpected increase in luminosity coincided precisely with its approach to a distance of roughly 2 astronomical units from the Sun, a point where astronomers anticipated a steady, predictable increase in brightness based on decades of observation. The core question that has been gnawing at the scientific community is both simple and deeply unsettling. Why? To truly grasp the significance of this anomaly, imagine it in human terms. Think of a weather forecast, predicting whether it will rain or shine, but on a cosmic scale. Astronomers use what they call a light curve to chart how bright an object like a comet should become as it approaches the Sun. These predictions aren't guesses made on a whim. They are carefully derived from years of detailed observations, sophisticated models of how ice sublimates in the vacuum of space, and an understanding of how dust particles scatter sunlight in complex ways. For several weeks leading up to this event, 3IATLAS had been following the expected script perfectly. Both professional astronomers and dedicated amateurs across the world tracked its gradual increase in brightness as it journeyed inward from the distant reaches of our solar system. Each measurement aligned with the predictions. Its luminosity grew steadily as the comet warmed, releasing gases and dust that formed its characteristic fuzzy atmosphere. This behavior was textbook, a predictable celestial ballet. But then between the 7th and 15th of September, a stark change occurred. Observers around the globe began reporting that the comet's brightness measurements were surpassing the anticipated values. The data points rose sharply, boldly deviating from the predicted trend line. In the language of astronomy, the object had jumped lanes. It was no longer conforming to the established pattern. When these brightness measurements are plotted on the standard magnitude scale used by astronomers, the deviation is unmistakable. The light curve, which had previously shown a smooth, predictable ascent, suddenly displays a steepened slope, a clear departure from the norm. It's as if someone had suddenly pressed the accelerator on a vehicle already cruising at highway speed, propelling it into uncharted territory. And here's where the mystery deepens. The scientific community is actively debating the cause of this sudden burst of brightness. Is it a real physical outburst, an unexpected and energetic release of gas and dust from the comet's nucleus? Or might it be something more technical, more mundane, what scientists call an aperture effect? This technical term refers to how different telescopes with varying sizes and observation methods can produce measurements that artificially inflate or distort the perceived brightness of an object. This latter explanation involves the understanding that the apparent increase in luminosity could simply result from the way observations are conducted, rather than any genuine change in the comet's activity. Different telescopes, with their specific apertures, essentially the size of their collecting lenses or mirrors, can capture varying amounts of light from the extended fuzzy atmosphere of the comet. If not properly calibrated or accounted for, these differences can lead to misleading measurements, making the comet appear unexpectedly brighter than it truly is. In summary, the ongoing debate centers around whether this sudden brightening is imagined trying to gauge the size of a distant campfire by observation alone. If you squint and peer through a narrow tube, you'll likely only see the brightest, most concentrated flames at the core, leading you to believe the fire is small but intensely hot. However, if you open your eyes wide and broaden your view, you'll suddenly become aware of the glowing embers and flickering lights that stretch far beyond your initial line of sight, revealing a much larger, more expansive blaze than first assumed. Similarly, when astronomers observe comets, different telescopes, each with varying sizes of apertures and detection methods, can experience comparable discrepancies. Some instruments might capture only the brightest central regions, while others detect the faint extended atmosphere that envelops the comet, known as the coma. The most reliable public data on these observations are compiled in a dedicated database called COBS, a vital resource for astronomers tracking these celestial visitors. When you glance at the latest charts from COBS, a vivid picture emerges. For the comet designated as 3IATLAS, the data traces a line that steadily climbs and then suddenly steepens in mid-September. This abrupt change in the brightness curve is unmistakable, even if scientists haven't yet reached a consensus on what it precisely signifies. To grasp the magnitude of what we're witnessing, consider the comet's incredible velocity. As it journeys inward toward the sun, 3IATLAS speeds along at tens of kilometers per second. Roughly 210,000 kilometers every hour. That's fast enough to cross an entire continent in less than a minute. As it approaches its closest point to the sun, known as perihelion, the press reports suggest its speed will peak at approximately 68 kilometers per second, an astonishing pace. This celestial rendezvous has been meticulously timed and precisely calculated. The perihelion is expected to occur in late October, specifically between the 29th and the 30th, at a distance of about 1.36 to 1.4 astronomical units from the Sun, just inside Mars's orbit. Speaking of Mars, this interstellar visitor will make a close pass by the red planet on October 3rd, coming within roughly 0.19 astronomical units. This proximity has attracted the attention of mission planners and scientists controlling spacecraft already orbiting Mars. Instruments like the high-resolution imaging science experiment called High-Resolution Imager, HiRISE, along with the color and stereo surface imaging system known as CASIS, and the high-resolution stereo camera, HRSC, are all preparing to seize opportunistic observations of this extraordinary object during its flyby. So, what is truly happening up there? The straightforward explanation in plain language is both simple and troubling. Either 3IATLAS is unexpectedly releasing an abundance of gas and dust, more than our models predicted, or our instruments are detecting a vast complex atmosphere surrounding the comet that has fooled our calculations, or perhaps both of these phenomena are occurring simultaneously. The implications of these possibilities reach far beyond mere academic curiosity. This is only the third confirmed interstellar object ever detected in our solar system. Unlike typical comets that originate from the Kuiper belt or the Oort cloud, regions with well-understood predictable orbital patterns, 3IATLAS hails from entirely different origins. Its behavior challenges the fundamental rules we have established through centuries of comet observations. Instead of following the expected patterns, this comet refuses to behave as a typical member of our solar system's small celestial bodies, hinting at underlying properties and origins that could redefine our understanding of objects from other star systems. The unexpected pattern of brightening in this interstellar visitor hints at a startling truth. Our grasp of such celestial objects remains woefully incomplete. Are we overlooking critical aspects of their behavior? Could it be that comets originating from distant star systems operate under principles fundamentally different from those of our familiar local specimens? The timing of these revelations couldn't be more compelling. As the interstellar wanderer known as 3IATLAS nears its closest approach to the Sun, every telescope, whether stationed on Earth or orbiting in space, is meticulously preparing to scrutinize this enigmatic visitor from the stars. What scientists uncover in the coming weeks could potentially revolutionize our understanding of the vast, largely uncharted regions of space that lie between stars. Yet the brightening anomaly is merely the opening act in a cascade of strange behaviors exhibited by this comet. One of the most perplexing phenomena is the rapid expansion of its fuzzy atmosphere, the comet's coma, forming into an enormous cloud that defies the laws of physics as we understand them. This cloud, which surrounds the nucleus of the comet, is ballooning at a rate that challenges the very foundations of cometary science. To appreciate why this is such a profound mystery, it's essential to understand what astronomers mean when they refer to a comet's coma. Think of the coma as the gaseous envelope that surrounds the comet's core, its atmosphere. But unlike Earth's relatively stable, gravitationally bound air envelope, a comet's coma is a chaotic, dynamic mixture of gases, dust particles, and plasma that extends outward into space, sometimes reaching hundreds of thousands of kilometers in size. This enormous, ever-changing cloud is formed when the ice on the surface of the comet heats up and sublimates, turns directly from solid into gas, carrying dust particles along with it. The result is a fuzzy, luminous cocoon that can dwarf planets in size, creating a stunning visual spectacle. On August the 6th in the year 2025, the James Webb Space Telescope turned its infrared sensors toward 3IATLAS and made a startling discovery. The comet's coma exhibited an unusually high concentration of carbon dioxide relative to water vapor. Such a chemical ratio is exceptional and suggests that this interstellar visitor either originated in an extremely cold region of its parent star system or underwent a chemical evolution vastly different from that of typical solar system comets. Why does this dominance of carbon dioxide matter so much? The key lies in the sublimation properties of different ices. Water ice requires significant solar heating to turn into gas, which generally occurs only when a comet ventures closer to the Sun. Conversely, carbon dioxide begins sublimating at much lower temperatures, meaning a comet rich in CO2 can become active and develop a coma far earlier during its approach. In the case of 3IATLAS, this meant it woke up in the outer reaches of our solar system, initiating its spectacular display much sooner than a typical comet would. Further analysis, utilizing near-infrared spectroscopy, revealed that this comet is enveloped in an extended carbon dioxide-dominated atmosphere stretching hundreds of thousands of kilometers into space. Some estimates suggest the total size of this gaseous envelope could reach approximately 700,000 kilometers, about half the diameter of the Sun. It's important to note, however, that these figures are preliminary estimates, not a conclusive scientific consensus. Different observational techniques and analytical methods can produce varying measurements, emphasizing the need for caution when interpreting these extraordinary observations. Nonetheless, this chemically unusual and physically immense atmosphere underscores just how alien and unpredictable this interstellar visitor truly is. The observations made by the Hubble Space Telescope during its session on July 21st added another intriguing piece to the complex puzzle surrounding this interstellar visitor. Their imaging revealed a densely packed nucleus entirely concealed beneath an exceptionally luminous cloud of dust, an opaque cocoon that obscures direct visual access to the core. By employing advanced brightness modeling techniques, astronomers were able to set an upper boundary on the nucleus's size, estimating it to be no larger than approximately 2.8 kilometers in radius. This measurement starkly contrasts with the inflated size estimates circulating widely on social media and various news outlets, which often claimed the nucleus was vastly larger, some suggesting diameters extending up to 5 or even 6 kilometers. Further validation of the nucleus's modest scale came from the Vera Rubin Observatory's Legacy Survey of Space and Time, which captured a series of images in June and conducted follow-up observations that placed the nucleus firmly within a size range of just a few kilometers across. Although some media reports have quoted diameters between 3 and 5.6 kilometers, scientists caution that these figures are fraught with inherent uncertainty. The true size remains a broad estimate rather than an exact measurement, emphasizing the difficulty in pinpointing the precise dimensions of such a distant, obscured object. Understanding the true nature of the comet's rapidly expanding surrounding envelope requires delving into the concept of dusty plasma. In simple terms, dusty plasma is a state of matter composed of neutral dust particles intertwined with gas molecules, many of which have become ionized under the influence of solar radiation. Unlike ordinary matter, this ionized material does not behave in a typical, predictable manner. Instead, it self-organizes into intricate dynamic structures, forming filaments, sheets, and pulses that seem to breathe and shift with a life of their own. When astronomers observe what appears to be living, organic patterns within the comet's coma, they are witnessing the fundamental physics of plasma self-organization at work. Magnetic fields threading through the ionized gas act as invisible highways, guiding the charged particles along well-defined pathways. These pathways give rise to the complex filamentary structures captured in high-resolution imagery, structures that resemble the natural phenomena of auroras dancing across polar skies or the massive loops of plasma seen erupting from the surface of the Sun. What makes the case of 3IATLAS particularly perplexing is the extraordinary combination of a colossal, rapidly expanding coma, rich in carbon dioxide, and its apparent behaviors. This particular chemistry and dynamic growth pattern defy easy classification. The first interstellar object, Oumuamua, showed no detectable cometary activity at all, behaving more like a tumbling asteroid. The second, Borisov, exhibited characteristics typical of a conventional comet, developing a visible tail and coma consistent with objects born in our solar system. Yet 3IATLAS appears to occupy a middle ground. It displays unmistakable signs of cometary activity, but its chemical makeup and physical behaviors are unlike anything expected from known comet categories. The dominance of carbon dioxide within its expanding atmosphere, coupled with the rapid growth of its coma and the unusual evolution in brightness, suggests that this object challenges the existing taxonomies used by astronomers. The rate at which the coma is enlarging raises fundamental questions about the underlying processes fueling its activity. Based on the amount of solar heating received at its current distance from the Sun, and considering the sublimation rates of various ices, models predict that the envelope should expand at a steady, predictable pace. However, observational data indicates that the coma is growing much faster than these standard models would suggest, hinting at the presence of some additional energy source or an underestimated mechanism driving the sublimation process. This discrepancy opens exciting avenues of scientific inquiry, as it may point to unknown physical phenomena or chemical properties that defy current understanding. Could the comet be generating internal heat through radioactive decay? While this idea might seem plausible at first glance, it remains highly unlikely given the comet's diminutive size. Radioactive heating requires a substantial volume of material capable of sustaining enough decay to influence surface activity, and a small nucleus simply cannot produce enough internal heat to account for the observed phenomena. But what if instead the comet is spinning so rapidly that it's creating internal stresses? Such intense rotation could potentially cause the surface layers to crack, exposing fresh, volatile, rich ice beneath. This process might lead to increased sublimation rates and unusual activity patterns. Although this is a conceivable scenario, it remains unproven and lacks direct observational evidence at this stage. Alternatively, the comet's composition could include exotic volatile materials that our terrestrial experience has yet to encounter or understand fully. This possibility opens the door to behaviors and reactions that defy conventional models, making the comet's activity even more enigmatic. Adding to the complexity is the plasma component surrounding the comet's expanding coma. As the solar wind, a continuous high-speed stream of charged particles emitted by our star, interacts with this swelling cloud of gas and dust, it creates a bow shock, much like the wake formed by a boat moving through water. This shock wave can accelerate the expansion of the coma and generate filamentary structures, giving the comet an almost living organic appearance. However, even when considering the effects of plasma interactions, the rate at which the coma is growing appears extraordinarily rapid. It's as if this interstellar visitor is operating under a different set of physical rules than the comets we have studied for centuries. The role of carbon dioxide chemistry offers part of the explanation. CO₂ sublimation begins at much colder temperatures than water ice, which could partly account for early activity. But it doesn't tell the full story. As we continue to observe this mysterious visitor approaching the inner solar system, each new piece of data only deepens the puzzle. The expanding envelope of gas and dust persists, fueled by sublimating ices that, according to our current understanding, shouldn't be so active at this distance from the Sun. Yet this isn't the only strange behavior exhibited by 3IATLAS. Throughout the summer months, astronomers have observed something even more startling. The color of the comet's coma has begun to shift, gradually taking on an eerie, vivid green glow, so striking it could easily inspire a science fiction scene. This phenomenon, known as fluorescing diatomic carbon, is well documented in astronomy but remains remarkable in its intensity here. In the dark, clear skies over Namibia during the eclipse nights of September 7th through the 17th, amateur astronomers captured stunning images of 3IATLAS glowing with an unmistakably vibrant green hue. The color was so vivid that it seemed almost artificial, stark against the star-studded backdrop of space. Green comets are not unprecedented. The characteristic green glow arises when diatomic carbon molecules, composed of two bonded carbon atoms, fluoresce under ultraviolet radiation from the Sun. These molecules absorb high-energy photons which excite them, and then re-emit this energy as visible light at approximately 518 nanometers, a wavelength our eyes interpret as green. Under normal circumstances, this process follows a predictable pattern. As a comet approaches the sun, increasing solar heat causes the breakdown of complex carbon-bearing molecules in the nucleus, leading to the formation of diatomic carbon. The intensity of this fluorescence typically correlates with the amount of solar radiation received and the abundance of carbon-based materials in the comet's composition. But in the case of 3IATLAS, the green glow doesn't fit the standard model. Its early and intense fluorescing suggests that something unusual is occurring within the comet's chemistry or physical state, challenging our current understanding of how these processes should unfold at its specified distance from the sun. Initial spectroscopic investigations indicated that the comet possessed an unusually high abundance of carbon dioxide, a trait that stood out sharply against the typical chemical makeup observed in other comets. Interestingly, these analyses also revealed that the signs of the classic carbon-based molecules responsible for producing the well-known green fluorescence were notably limited. Under normal circumstances, such a chemical profile would suggest that any green glow should be relatively weak or delayed, manifesting only after the comet had approached closer to the sun and undergone sufficient heating. Yet what observers actually saw was quite different. The comet's green fluorescence appeared earlier and with greater intensity than what these chemical expectations would predict given its current distance from the sun and its peculiar composition. This discrepancy caught the scientific community by surprise, prompting intense interest and ongoing investigation. The phenomenon appeared to defy the anticipated chemistry, as the comet seemed to be turning green sooner and more vividly than models indicated it should. A clear sign that some aspect of its behavior or internal chemistry remained unaccounted for. Understanding why this matters requires a closer look at the subtle and delicate chemical processes taking place within the comet's coma. The vast, hazy envelope of gas and dust that surrounds its solid nucleus. As the comet approaches the sun, the solar radiation heats the nucleus, causing various volatile materials to sublimate, transform directly from solid into gas, at different temperatures and at different distances from the star. Water ice, for example, requires significant heating and thus sublimates at relatively closer distances, whereas carbon dioxide, being more volatile, begins turning into gas much earlier during the approach. As this volatile sublimation occurs, complex molecules containing carbon, such as hydrocarbons, begin to break down into simpler constituents at various stages, releasing energy and creating conditions ripe for fluorescence. The green glow that we observe is primarily the result of these carbon-bearing molecules being excited by solar radiation, causing them to emit light at specific wavelengths associated with diatomic carbon and similar species. The key point here is that the timing of this green fluorescence, its onset and its strength, should align closely with our understanding of the comet's chemistry and the heating it experiences. However, the fact that the green glow is occurring earlier and more intensely than models suggest indicates that something unusual is happening. It's as if the internal chemistry of the comet, or perhaps the way solar energy interacts with its materials, is different from what we've encountered before. One plausible explanation is that the comet contains types of carbon chemistry that are unknown or not properly accounted for in current models. Alternatively, the process of solar heating might be affecting its materials in ways that are not yet understood, causing chemical reactions to occur more rapidly or efficiently. As the comet continues its inward journey, the chemical landscape of its coma is likely to change dramatically. With increasing solar heat, molecules that were once stable at larger distances from the sun could begin to break apart more quickly, giving rise to new chemical species that fluoresce differently. This chemical transition could explain the unusually early and intense green emissions, representing a rapid or extensive shift in the comet's molecular makeup, happening sooner than standard models predict. It's as if the comet has an exotic or atypical chemistry that responds to solar energy in a way that we haven't yet observed in other objects. It's important to clarify that the green coloration does not imply that the solid nucleus of 3I₄ itself is green. The core remains a dark, rocky mixture of ice and dust, probably reddish or brownish, similar to many other comets and asteroids. The green glow arises solely from the surrounding gas envelope, which extends thousands of kilometers into space. This distinction is crucial because it underscores that the fluorescence is a property of the coma's gaseous molecules, not the solid body at its heart. When the coma thickens with gas and dust, particularly if molecules like diatomic carbon become more abundant, the green fluorescence naturally becomes more prominent. In fact, these two phenomena, the rapid brightening of the green fluorescence and the overall brightness increase of the comet, are likely interconnected, both stemming from the same fundamental process. Think of it as similar to neon signs lighting up with an electrical surge. The internal chemistry of the comet appears to be accelerating, powered by solar radiation that causes reactions to occur more swiftly and intensely than our existing models had anticipated. The green glow thus becomes a visible indicator that the comet's internal chemical activity is ramping up at a pace that suggests novel or previously unobserved processes are at play, perhaps involving exotic molecules or unique interactions with solar energy, challenging our current understanding of cometary physics and chemistry. Interpreting the visual evidence of this enigmatic comet demands a cautious approach, as appearances can be deceiving. Modern digital cameras and image enhancement techniques have the remarkable ability to amplify colors and details far beyond what the human eye perceives during direct observation. The vivid green photograph that has been circulating widely online, for instance, may portray an intensity of color that exceeds what one would see through a telescope's eyepiece. This discrepancy arises because digital processing can artificially heighten certain hues, creating a striking visual effect that captures the imagination. However, amid these enhancements, the fundamental physics remain unchanged. The spectral signature at approximately 518 nanometers is a real, measurable phenomenon, an authentic indicator that diatomic carbon molecules are fluorescing within the comet's coma. This emission line is a well-understood consequence of chemical excitation caused by solar ultraviolet radiation, confirming that the green glow is not merely an optical illusion, but a genuine space-based process. Furthermore, this intense green fluorescence offers valuable insights beyond mere coloration. It can serve as an indicator of the comet's rotation and internal architecture. If 3I₄ spins rapidly, different sections of its surface would be alternately exposed to the sun's rays, leading to fluctuating levels of solar heating across its surface. Such dynamic exposure could result in variations in the intensity and spatial distribution of the green fluorescence over time. Indeed, some observers have reported noticing subtle changes, shifts in brightness and the extent of the green coloration, over hours or days. These observations suggest that the comet's nucleus might be spinning, exposing different regions of its surface to sunlight and thus influencing the chemical reactions taking place within its coma. The psychological impact of this eerie green glow cannot be overstated. Throughout human history, celestial phenomena that display unusual colors or shapes have often evoked awe, wonder, and sometimes anxiety. A comet glowing with such a distinctive green hue, especially one originating from beyond our solar system, naturally sparks thoughts of the alien and the otherworldly. Science fiction narratives have long associated green lights with exotic technology or extraterrestrial intelligence, reinforcing a cultural subconscious that links unusual space phenomena with the possibility of alien encounters. Yet, from an astronomical perspective, nature has repeatedly demonstrated that it can produce phenomena far more spectacular and bizarre than the most imaginative science fiction scenarios. The green glow of 3IATLAS, while striking in its timing and intensity, is rooted in real chemical processes unfolding under the extreme conditions of space, processes that can be understood through the laws of physics and chemistry. This comet essentially functions as a natural laboratory, a celestial experiment where materials from another star system are subjected to our sun's radiation, leading to heating, chemical transformation, and dynamic activity. As 3IATLAS continues its inward journey toward perihelion, the closest point to the sun, the green fluorescence is expected to intensify further. Increased solar radiation will likely accelerate the breakdown of complex carbon-bearing molecules, potentially creating even more dramatic visual displays of fluorescence and emission. Meanwhile, amateur astronomers around the world are persistently documenting these evolving phenomena, providing invaluable observations that contribute to our scientific understanding of this interstellar visitor. Their efforts help fill in the gaps that professional telescopes might miss, especially during times when access to high-resolution imaging is limited. Among the many unusual aspects of 3IATLAS's appearance, the green glow stands out as perhaps the most visually arresting. It complements other anomalies such as the rapid expansion of the comet's coma and its unexpected brightening, all of which collectively suggest a kind of behavior that challenges our conventional understanding of cometary physics, something that doesn't quite fit the patterns established by countless previous observations. Yet amidst these remarkable features, one particular geometric peculiarity has left astronomers scratching their heads and conspiracy theorists working overtime. Specifically, there is something about the orientation of the comet's tail that appears to defy the basic physics governing how comets are expected to interact with the solar wind. This brings us to what is known as the anti-tail and the strange, seemingly contradictory geometry of this celestial object. Normally, a comet's tail is shaped by the relentless push of solar radiation and the solar wind, which together create a characteristic configuration. Dust particles are blown away from the nucleus, forming a curved dust tail that points roughly away from the sun, while ionized gases are swept into a straight, narrow ion tail that also points sunward, directly opposite to the incoming solar particles. This predictable pattern has been observed in countless comets, from ancient times to modern space missions, and is considered a fundamental aspect of comet behavior in our solar environment. However, observations of 3IATLAS have revealed something unprecedented, a feature known as an anti-tail. Instead of the tail pointing away from the sun, a spike of dust and gas appears to be directed toward the star itself. At first glance, this seems to violate the basic principles of physics, raising questions about whether the comet is somehow defying the solar wind's influence. But the explanation lies not in any exotic propulsion or unknown force, but rather in perspective and geometry. Many such apparent anomalies are. In the well-established framework of cometary behavior, the appearance of tails is typically predicted and understood with remarkable consistency. The classic image we hold of a bright comet shows tails that always point directly away from the sun, shaped by the relentless push of solar radiation and the continuous outflow of charged particles streaming outward in what is known as the solar wind. These are the fundamental forces that sculpt comet tails into their familiar forms. This principle, that tails always point away from the sun, has been a steadfast rule since humanity first observed comets, from the ancient appearances of Halley's Comet to the dazzling displays witnessed in recent times. To fully appreciate why the behavior of comet tails is so important, it's essential to understand the underlying physics behind their formation. When a comet journeys closer to the sun, the intense solar energy heats its icy nucleus, causing sublimation, the direct transformation of ice into gas. This process creates a surrounding cloud of gas and dust called the coma. Solar radiation pressure, exerting a gentle but persistent force, pushes tiny dust particles outward from the nucleus, forming a curved dust tail that generally follows the comet's orbital trajectory. At the same time, the solar wind, a steady high-speed stream of charged particles emanating from the sun, ionizes the gas molecules in the coma, turning them into charged plasma that is swept away by this outward flow, forming a second tail known as the ion tail. This ion tail is typically straight and points directly away from the sun, aligned with the direction of the solar wind. The combination of these two effects, the curved dust tail and the straight ion tail, creates the characteristic appearance most associated with bright, spectacular comets. The physics behind this is straightforward. Both dust particles and ionized gases follow the path of least resistance under the influence of solar forces, which predominantly push material away from the sun. Since the sun's influence is the strongest, everything flows outward, away from our star, producing the familiar tail orientation. However, recent early observations of the interstellar comet 3IATLAS challenge this long-held understanding. Instead of observing tails that conform to the expected pattern, astronomers detected something exceptional: a plume pointing toward the sun, an odd phenomenon known as an anti-tail. Rather than material streaming away from the sun, a spike of dust and gas appeared to be heading directly back toward our star, an apparent defiance of the physical forces at work. Before jumping to conclusions about anti-gravity effects or alien propulsion systems, it's crucial to recognize that anti-tails, while visually dramatic and seemingly paradoxical, can be explained through natural causes. They are primarily illusions resulting from the geometry of viewing the comet in three-dimensional space. Imagine looking at a thin sheet of dust particles from Earth. If this sheet extends both toward and away from the sun, our vantage point can align with a specific angle where the sunward portion appears projected against the sky. In such a perspective, the dust sheet can create the illusion of a tail pointing toward the sun, even though physically the dust is still being pushed away from it. Essentially, the anti-tail is a trick of perspective, a visual illusion born from how we observe the comet in 3 dimensions. The complexity of this effect is heightened when considering the particular orbital path of 3I-ATLAS. Unlike most comets, which follow prograde orbits, moving in the same direction as the planets around the sun, this comet follows a nearly retrograde trajectory inclined at approximately 5 degrees relative to the ecliptic plane, the flat, disc-shaped region where most planets orbit. This unusual inclination enhances the potential for perspective effects, making the anti-tail phenomenon more pronounced and challenging to interpret. Later, additional observations, including a striking image captured by the Gemini South Telescope on August 27th, revealed a more conventional tail pointing away from the sun, in line with the standard physics. This more typical tail confirms that the anti-tail effect was largely a matter of perspective and viewing angle, rather than an actual reversal of the physical processes governing comet tails. The earlier observation of a sunward-facing plume had already begun to draw considerable attention, fueling widespread speculation about the comet's extraordinary nature. This effect was further illuminated through the technique of polarimetry, a sophisticated method that examines how light waves are affected as they scatter off dust particles within the comet's atmosphere. By analyzing the polarization of this scattered light, scientists uncovered additional layers of complexity in the structure of 3I-ATLAS's tail. The measurements indicated that the dust and plasma surrounding the comet's nucleus are organized in a highly structured, perhaps even orchestrated manner. This organization does not align with the straightforward models typically employed to describe comet tails, which often assume simple, roughly spherical or elongated distributions of gas and dust. Instead, the polarimetry results point to a far more intricate architecture within the comet's coma, a dynamic, complex arrangement of gas and debris that defies the common, more uniform patterns observed in most other comets. Visualize it as the difference between a smooth, spherical balloon, one that's uniform and uncomplicated, and an elaborately folded origami sculpture, crafted with the same basic material but showcasing an astonishing level of structural sophistication. The comparison highlights how the internal organization of the dust and plasma around 3I₄atlas's nucleus is remarkably more elaborate than the typical, more predictable configuration seen elsewhere. Adding to the enigma is the so-called anti-tail phenomenon, an unusual feature that, combined with the comet's high velocity and its peculiar orbital inclination, creates a breathtaking visual spectacle that naturally stirs suspicion. To casual sky watchers and even to some seasoned astronomers, the comet appears to be challenging the fundamental forces that govern celestial motion within our solar system. It looks as though it is somehow resisting or defying the expected push of the solar wind, which is responsible for shaping most comet tails. This apparent rebellion against natural laws feeds into the human fascination with the extraordinary, often leading to the temptation to interpret such phenomena as signs of something artificial or engineered. When we encounter events that seem to violate basic physics, like a comet seemingly pushing back against the solar wind, the human mind tends to reach for more dramatic, perhaps even speculative explanations. Could it be a propulsion system of some sort secretly powering the comet instead of it just being a natural icy body? Nevertheless, the reality, as is often the case in astronomy, is more nuanced and subtly fascinating than any of the more exotic theories suggest. The so-called anti-tail is actually a manifestation of the same geometric principles that produce optical illusions here on Earth. For example, a straight road can appear to curve when viewed from certain angles, or distant mountains can seem to float above the horizon under specific atmospheric conditions. The anti-tail of 3I₄atlas is a similar optical illusion, an authentic natural phenomenon, arising purely from perspective and geometry. The comet's nearly flat orbit, closely aligned with the plane of the ecliptic, the flat disc-shaped region where most planets orbit, plays a critical role in amplifying these perspective effects for observers on Earth. As the comet moves through the three-dimensional expanse of space, different parts of its vast, extended envelope of gas and dust become visible or hidden, depending entirely on our vantage point. What appears to be a tail pointing directly toward the sun may in fact be a visual artifact caused by the specific viewing angle, revealing only certain components of the comet's material. The material flowing in multiple directions, some parts away from the sun and others toward it, may be all present simultaneously, but only certain segments are visible from our perspective. Understanding this anti-tail phenomenon requires active three-dimensional thinking, as opposed to simply interpreting flat two-dimensional images. It's akin to observing shadows cast on a wall and attempting to deduce the shapes and orientations of the objects that create them. The shadows, the two-dimensional projections, are real, but their interpretation depends heavily on understanding the geometry and perspective involved. As 3I₄atlas continues its approach toward perihelion, the closest point to the sun, its anti-tail behavior is likely to evolve, shifting and changing as new parts of the dust and gas envelope come into view or recede from sight. This dynamic will provide further insight into the true nature of the comet's structure and the physical processes at play. At different angles of observation, various parts of the comet's expansive atmosphere may either come into view or fade into obscurity, potentially unveiling surprising new geometric configurations. This variability presents a significant challenge for astronomers. They must carefully differentiate between actual physical abnormalities in the comet's structure and mere optical illusions created by the perspective from which they observe. The phenomenon of the anti-tail exemplifies this perfectly. It demonstrates how 3IATLAS can appear distinctly alien, yet in reality it adheres strictly to the fundamental physical principles governing cometary behavior. Its unusual visual traits are the result of a complex interplay of authentic chemical and physical peculiarities, amplified and distorted by viewing angles that exaggerate its strangeness. However, when comparing these perspective-driven illusions to one of the most extraordinary features of 3IATLAS, something that has genuine scientists exclaiming words like unprecedented and anomalous, the differences become stark. The way this comet polarizes light stands out as something entirely novel. The polarization signatures observed do not match any known profiles from objects within our solar system or beyond it. These unique signals suggest that the dust and gas surrounding the comet are scattering light in ways that defy current scientific understanding, hinting at potentially exotic material compositions or physical processes that we have yet to comprehend fully. Part 5. A swarm in the skies. The autumn of 2025 has transformed Earth's night sky into a veritable cosmic traffic jam. Several luminous comets are traversing the inner reaches of our solar neighborhood simultaneously, creating a spectacle of celestial brightness and motion that has not been seen in many decades. At the heart of this celestial assembly, 3IATLAS makes its path, like a visitor from another star system, cutting through the darkness with a presence that seems almost surreal. It is accompanied by a supporting cast of other comets, many of which originated much closer to home, within our solar system, yet now appear together in the same sky. The timing of these arrivals is particularly remarkable, as it appears to be a confluence of cosmic events that, by chance or design, have synchronized to produce a dazzling display. For instance, Comet R2 Swan reached its closest approach to the Sun on September 12th and is expected to pass near Earth around October 21st, coming within approximately a quarter of an astronomical unit, roughly 23 million miles. This proximity is close enough that, under dark sky conditions, it might even be visible to the naked eye. Another comet, designated 414P Stereo, a periodic visitor that completes its journey around the Sun every 7.5 years, arrived at perihelion on September 27th, traveling at about half an astronomical unit from the Sun. It adds yet another bright point to the autumn sky. Perhaps the most anticipated is Comet A6 Lemon, predicted to reach an apparent magnitude of 3 to 4 as it approaches perihelion on November 8th, at about half an astronomical unit from the Sun. This brightness level could make it visible even from locations affected by moderate light pollution, offering a spectacular view without specialized telescopes. To comprehend how multiple comets can grace our skies simultaneously without any physical connection, one might imagine cars traveling on different highways, converging on a single city from various directions. Each comet follows its own orbital path, separate routes that, by coincidence, bring them into the inner solar system during roughly the same period. This apparent coordination is purely a product of orbital mechanics and observational bias, not any underlying relationship between the objects. Comets only become visible from Earth when they venture close enough to the Sun, causing their icy nuclei to develop substantial coma and tails. Additionally, they must be positioned in parts of the sky that are dark enough for observation, away from the Sun's glare, so that their brightness and structure can be properly seen and studied. This interplay of celestial mechanics and observational conditions creates a temporary, yet spectacular clustering of bright comets in our night sky, a visual reminder of the dynamic and often coincidental dance of objects within our solar system. The apparent clustering of multiple bright comets in our night sky might initially suggest a remarkable coincidence, yet statistically, it aligns more closely with the natural patterns of cometary orbits, rather than indicating any direct connection among the objects themselves. In other words, what we observe as a sudden influx of luminous visitors from the cosmos is likely a consequence of the predictable dynamics governing their trajectories, rather than evidence of an orchestrated event or a shared origin. However, this celestial gathering in the autumn months is only one facet of the intense activity that has marked recent weeks. Throughout mid-September, the night skies became the focus of heightened attention as a series of asteroid close approaches unfolded in rapid succession. These events captured headlines and fueled discussions across social media platforms, contributing to a renewed sense of cosmic activity and potential peril. The standout among these was the close pass of asteroid 2025 22 on September 18th. Despite the fact that this asteroid remained entirely safe, passing at a distance of several million kilometers, far enough away to pose no threat, the encounter garnered significant media coverage and was a trending topic online. The reason for this heightened interest was not solely the event itself, but the timing and nomenclature. The asteroid's designation, featuring the year 2025, inadvertently evoked thoughts of future threats and set the scene for a narrative of imminent danger. Its passage coincided with ongoing comet activity, amplifying public awareness about objects traversing Earth's neighborhood. During this period, several smaller asteroids also made their own close yet still safe approaches. Each of these flybys briefly captured media attention, collectively contributing to a perception that September 2025 was an extraordinarily active month for near-Earth objects. Yet beneath this perception lies a more mundane reality. Such close encounters are not rare. They happen with regularity. The vast majority of asteroid flybys go largely unnoticed by the general public because they occur at distances that do not threaten Earth and are often too subtle to register without specialized telescopic equipment. The recent wave of activity, therefore, is primarily a reflection of the enhanced capabilities of modern sky surveys, which can detect smaller and more distant objects than ever before. This technological progress has resulted in a higher volume of identified near-Earth objects, creating the illusion of an unusual spike in activity, an effect amplified by our increased vigilance. Nevertheless, the psychological impact of witnessing multiple asteroid and comet events in a compressed time frame cannot be dismissed. Human cognition is inherently pattern-seeking. When confronted with several seemingly related phenomena occurring close together, our minds tend to infer connections, even when none exist. This tendency becomes especially pronounced in the context of celestial phenomena, which have historically been interpreted as omens, messages, or signs foretelling significant earthly or cosmic events. Throughout history, unusual alignments or appearances of comets, planets, and other astronomical configurations have inspired fears, superstitions, or messages from the divine. Today, in the midst of an apparent surge of comet and asteroid activity, this psychological response is once again activated. The timing and clustering of these events prompt questions and speculations that extend beyond the purely scientific. For those inclined toward more extraordinary interpretations, it raises provocative possibilities. Could an advanced extraterrestrial civilization be intentionally dispatching reconnaissance probes into our solar system? If so, might they coordinate their arrival to coincide with the natural, predictable chaos of cometary swarms? Such camouflage would be a masterstroke, allowing artificial objects to blend seamlessly into the cosmic background, effectively cloaking their true nature. The logic behind this hypothesis is compelling. Natural comet swarms tend to appear periodically, driven by gravitational perturbations in the distant reaches of the solar system. These perturbations, caused by the gravitational influences of planets passing stars or other celestial bodies, occasionally send multiple objects on sun-approaching trajectories within short spans of time. if an intelligent civilization aimed to observe or monitor our solar system covertly, integrating their probes into such natural phenomena would be an astute strategy. By aligning their arrivals with periods of increased cometary activity, they would minimize the risk of detection, exploiting the inherent chaos and the limitations of our observational focus. In essence, this scenario suggests that the universe's most natural and seemingly coincidental pattern, an influx of bright comets and close-approaching asteroids, could in theory serve as an elaborate cover. Such a strategy would allow advanced civilizations to conduct reconnaissance while remaining hidden behind the veil of natural celestial activity. This concept, while speculative, underscores the importance of considering not only the physics of the objects themselves, but also the broader context of how and when they appear. It raises profound questions about the nature of cosmic observation, the potential for extraterrestrial intelligence, and the subtlety with which advanced civilizations might operate in our cosmic neighborhood. Any artificial objects entering our solar system during such busy periods would blend seamlessly into the cosmic crowd, indistinguishable from natural phenomena, and thus less likely to receive detailed scrutiny. This makes the notion of deliberate reconnaissance particularly compelling, especially when considering the characteristics of certain orbital paths that could be deliberately chosen to maximize observational advantage. For instance, a trajectory that brings an object close to multiple planets would offer an unprecedented opportunity to study various worlds within a single mission. An idea that is both strategically elegant and scientifically advantageous. Take the case of 3IATLAS. Its current path will bring it in relatively close proximity to Mars, enabling high-resolution observations of the planet's surface and atmosphere before it continues its inward journey toward perihelion, its closest approach to the Sun. From a strategic standpoint, this timing is far from coincidental. The current cosmic environment, teeming with bright comets and other celestial objects, provides an ideal cover for covert surveillance activities. The sky is already crowded with dazzling objects, making it easy for an anomaly, whether natural or artificial, to go unnoticed or be dismissed as routine. The widespread public and scientific focus on these prominent events further diminishes suspicion, allowing subtle or deliberate observations to proceed under the radar. Of course, the most straightforward explanation remains that these are natural phenomena. Gravitational interactions in the distant reaches of the solar system frequently dislodge multiple comets simultaneously, sending them on inward trajectories that overlap in time, creating what we observe as natural swarms. Improvements in survey technology have made it possible to detect objects that have always been present but previously remained unseen, revealing a bustling, dynamic environment filled with celestial debris. The recent appearance of several asteroids and comets, now more visible thanks to enhanced detection capabilities, exemplifies this routine process. However, as 3IATLAS advances toward the inner solar system, its uniqueness becomes increasingly apparent. Its interstellar origin, combined with its atypical properties, such as its chemical composition, rapid activity, and unusual tail behavior, raises the question of whether we are simply witnessing a cosmic coincidence or if something more deliberate is at play. The answer becomes even more intriguing when examining the way this object reflects and polarizes sunlight. Its polarization signatures are so unusual that some scientists are struggling to find natural explanations that fully account for what they observe, pushing the debate into the realm of the potentially artificial. This leads us to a fundamental question haunting astronomers in the year 2025. Is 3IATLAS a natural object exhibiting phenomena we have yet to understand? Or does it challenge our assumptions about what can exist in interstellar space? To explore this, we must look back at the two previous confirmed interstellar visitors that entered our solar system. Objects whose behaviors and compositions have already pushed the boundaries of our understanding. The first of these, known as Oumuamua, discovered in October of 2017, shattered expectations by exhibiting no obvious signs of cometary activity, despite following a hyperbolic trajectory that unmistakably indicated an origin beyond our solar system. Unlike typical comets, which develop a glowing coma and tail as they approach the sun due to sublimation of ices, Oumuamua remained stubbornly inert, looking more like a tumbling asteroid than an icy visitor. Its lack of a visible coma was puzzling enough, but what truly raised eyebrows was a slight but measurable acceleration, an unexpected push that could not be explained by gravity alone. This anomaly prompted a flurry of hypotheses ranging from unconventional natural explanations to the provocative notion that Oumuamua might be an artificial probe or craft, deliberately designed or modified by an extraterrestrial civilization. The second interstellar object, known as Borisov, discovered in August of 2019, presented a stark contrast. It behaved very much like a typical comet from our solar system, developing a prominent coma and tail as it approached the sun. Spectroscopic analyses revealed a composition similar to comets originating from our local stellar neighborhood, suggesting that the processes of comet formation might be more universal than previously thought. Borisov's behavior and chemistry aligned well with established natural models, providing a baseline for what a natural interstellar comet could look like. Now, 3IATLAS occupies a liminal space between these two extremes. It displays clear cometary activity. Its brightness and tail behavior suggest an icy, volatile, rich body, yet its chemical makeup, rapid expansion, and polarized light signatures seem to defy conventional understanding. Its composition appears dominated by carbon dioxide, and its activity levels seem unusually high given its current position relative to the sun. Additionally, its polarization measurements, how it reflects and polarizes sunlight, are so extraordinary that they prompt questions about whether its surface materials are natural or artificial in origin. These anomalies collectively challenge our existing categories and models. The size of its nucleus, for example, has been constrained by high-resolution observations to be relatively small, around 2 to 3 kilometers in radius. Yet it exhibits an enormous, rapidly expanding coma that seems disproportionate for such a modest core. The chemical ratios, especially the dominance of carbon dioxide, hint at formation in extremely cold regions, perhaps in the outer reaches of this unexpected acceleration, ignited fervent debate within the scientific community, fueling speculation about the possibility of artificial origins. If the object were indeed a discarded spacecraft, perhaps equipped with residual outgassing or even some form of exotic propulsion system, then such acceleration could be more easily rationalized. In that scenario, it would suggest an engineered craft harnessing mechanisms beyond our current understanding of natural physics. However, when considering a natural celestial body, explaining this acceleration becomes markedly more challenging. For example, the interstellar object Oumuamua, discovered in August 2019, presented a stark contrast to this case. That object behaved precisely like a textbook comet, developing a substantial coma and tail as it approached the sun. Spectroscopic analyses of Oumuamua revealed compositions remarkably similar to comets native to our solar system, implying that the processes responsible for comet formation may be broadly universal, occurring similarly across different star systems regardless of local conditions. Now, 3IATLAS, the current interstellar visitor, appears to occupy an ambiguous position along this spectrum. It displays unmistakable cometary features, a visible fuzzy atmosphere, a tail, and rapid sublimation activity. Yet its chemical and physical properties do not align neatly with the expectations derived from either typical solar system comets or the previously observed interstellar objects. Notably, its composition is rich in carbon dioxide, an unusual trait that defies straightforward classification. Adding to the complexity are its peculiar polarization properties and the remarkably swift expansion of its coma, factors that together challenge the tidy categories of celestial bodies we have established. One of the critical issues lies in estimating the size of its nucleus, a parameter that directly influences how we interpret many of its other behaviors. Observations from the Hubble Space Telescope set an upper limit for the nucleus radius at approximately 2.8 kilometers, which corresponds to a diameter of less than 5.6 kilometers. Meanwhile, various ground-based surveys suggest the actual size likely falls within a range of a few kilometers, decisively ruling out the early speculative notion of a 50-kilometer-sized monster. This size constraint is vital because it limits the total amount of volatile material the nucleus can contain. A smaller nucleus simply cannot sustain the level of activity observed, such as the rapid coma growth and brightening, unless its activity is extraordinarily efficient or its composition differs significantly from that of typical comets. If the comet's activity appears disproportionate to its size, it raises the possibility that unconventional processes are at work or that our models need refinement. When the observed behaviors are so difficult to reconcile with natural explanations, the allure of an artificial origin becomes more compelling. The unusual combination of a small nucleus, vigorous activity, and exotic chemistry suggests, at least on the surface, that 3IATLAS might be more than just a natural object. It could, in theory, be an engineered artifact, perhaps more easily explained by intelligent design than by chance. Nevertheless, established scientific principles, particularly Occam's razor, advocate for the simplest explanation that can account for all the observed phenomena. This principle advises us to prefer natural explanations unless the evidence strongly indicates otherwise. Accordingly, astronomers diligently explore every conceivable natural mechanism that might produce these anomalies. Among these are the possibilities that the comet's volatile composition is significantly different from that of bodies formed within our solar system. For instance, an early onset of activity and unusual chemical signatures might be attributable to formation in a colder, more remote region of its original star system, where different processes dominate. Such a composition could involve an abundance of carbon dioxide ice, which sublimates at greater distances from the star, thus explaining why the comet became active earlier than expected. In essence, the peculiarities of 3IATLAS could still be explained through natural processes, albeit extreme or uncommon ones. Underscoring the importance of considering all natural scenarios thoroughly before leaping to conclusions about artificial origins. The surface texture and internal structure of the comet's nucleus can significantly influence how effectively it releases gases and dust when warmed by the sun's radiation. Variations in surface roughness or the presence of layered or uneven terrain could create zones where sublimation occurs more readily, thus affecting the overall activity level. Additionally, if the comet is spinning rapidly, centrifugal forces might play a crucial role by helping to eject material from its surface, especially from regions where the structural integrity is compromised. This rapid rotation could also cause surface stresses that lead to fractures or the exposure of fresh, volatile-rich layers, areas where ices and other volatile compounds are more accessible to solar heating, thus fueling increased outgassing. Internal fracturing or fragmentation presents another compelling mechanism. When the comet's core is broken or split, it can reveal previously shielded pockets of volatile material that have remained untouched since formation. These newly exposed regions would then interact intensely with solar radiation, resulting in sudden spikes in activity or changes in the composition of the surrounding atmosphere. The advanced imaging techniques discussed earlier, particularly polar imagery, offer especially powerful diagnostic tools for unraveling these mysteries. When sunlight reflects off dust particles within a comet's coma, The orientation of the reflected light waves encodes critical information about the physical characteristics of those particles. By analyzing the polarization of this reflected light, essentially how the light waves are oriented after bouncing off the dust, astronomers can infer details about the size, shape, and surface properties of the scattering particles that are not readily apparent from mere brightness measurements. What makes the polarization data from 3IATLAS particularly intriguing is that it exhibits characteristics unlike any observed in other solar system objects, whether comets, asteroids, or similar bodies. Specifically, the comet shows extreme negative polarization values at small phase angles. For instance, at approximately 7 degrees, the polarization dips to a minimum of around negative 2.7%, a level of measurement that is unprecedented. Such anomalies challenge our current understanding of how dust grains scatter light and suggest that the properties of the comet's dust are highly unusual. These polarization peculiarities could be indicative of dust particles with exotic properties. For example, irradiation during the comet's long voyage through interstellar space might have altered the dust grains, resulting in unique optical characteristics. Alternatively, the composition of the dust may be fundamentally different from that of typical solar system objects, possibly involving materials formed or modified under conditions not encountered locally. There is even the provocative possibility that some of the scattering particles might be artificial in origin, crafted from materials with optical properties unlike any naturally occurring substances known to science. The significance of these findings has not gone unnoticed among credible researchers and scientific commentators. Perspectives shared through academic blogs and preprint repositories acknowledge the strange nature of the polarization signals, emphasizing the importance of cautious interpretation. While these anomalies are genuine and represent a compelling scientific puzzle, the principle of scientific rigor demands that extraordinary claims, such as the presence of artificial materials, be supported by correspondingly extraordinary evidence. The hypothesis that this comet could be of artificial origin encounters numerous substantial challenges. For one, despite concerted efforts by multiple observatories, no confirmed radio emissions or other signals indicative of artificial intelligence or communication have been detected from 3IATLAS. Its trajectory, although unusual, remains consistent with the laws of gravity and celestial mechanics, showing no signs of active course corrections or maneuvers that would suggest controlled propulsion or intervention. This stability implies the comet's movement can be explained by natural gravitational influences without invoking exotic propulsion systems. Furthermore, if 3IATLAS were indeed an artificial construct, it would represent technology operating on a scale and time span that significantly surpasses human capabilities. Its journey from its home star system to our solar system would have taken thousands, perhaps tens of thousands of years, assuming it traveled at speeds comparable to our fastest spacecraft. Such an achievement would imply a civilization with technological prowess far beyond our own, capable of long-term interstellar missions spanning multiple generations. From a scientific standpoint, the more conservative and parsimonious explanation involves expanding our understanding of comet physics and interstellar chemistry. This approach does not require assuming the existence of alien technology. While the properties exhibited by 3IATLAS, such as its rapid activity, unusual chemical signatures, and polarization features, push the boundaries of what we previously considered possible for natural objects, they do not definitively prove an artificial origin. Instead, they suggest that our knowledge of interstellar materials and cometary behavior may still be incomplete, and that the comet's peculiarities could be explained by exotic, yet entirely natural processes yet to be fully understood. As ongoing observations continue to shed new light and more comprehensive data accumulates, the scientific community will steadily work toward identifying the most plausible explanation for the peculiar and seemingly inexplicable characteristics exhibited by 3IATLAS. This process, inherently meticulous and often lengthy, may span months or even several years. Still, over time, the cumulative weight of evidence, derived from spectroscopy, imaging, and orbital data, will inevitably tilt the balance, leading us to accept either the notion of an exotic natural phenomenon or something far more extraordinary. The importance of reaching a definitive conclusion extends well beyond mere academic curiosity. It probes the very essence of our understanding of the universe and our place within it. Should 3IATLAS ultimately be confirmed as artificial, an object of technological origin from beyond our solar system, it would mark a historic milestone, the first incontrovertible evidence of contact with extraterrestrial technology. Such a discovery would revolutionize humanity's conception of our cosmic environment, forcing us to reevaluate our assumptions about life, intelligence, and technological achievement on a galactic scale. However, before jumping to such revolutionary and potentially paradigm-shifting conclusions, it is prudent to examine whether 3IATLAS might be part of an even larger, more complex phenomenon. What if this comet isn't an isolated interloper, but rather a fragment of a vast and ancient cosmic debris field, scattered across interstellar space by cataclysmic events long past? This leads us to consider the debris field hypothesis, a compelling theory that sometimes offers the most plausible explanation for unusual celestial objects. Part 7 of this exploration delves into the debris field hypothesis, a scenario that recognizes that some of the most extraordinary phenomena in the universe often originate from the aftermath of catastrophic events. Imagine the possibility that 3IATLAS, along with other anomalous objects detected in our skies, are remnants, detritus from a colossal cosmic disaster that took place thousands, perhaps millions of years ago in a distant star system. The implications of such a hypothesis stretch the limits of our imagination, yet they remain comfortably within the boundaries of known physics. Debris fields can indeed be ejected from star systems through a variety of mechanisms, each capable of propelling material across the vast expanses of interstellar space with velocities sufficient to eventually bring these fragments into our own neighborhood. One of the primary processes involved in creating such debris fields is the chaotic phase of planetary formation. During this tumultuous period, massive planetary bodies often collide, fragment, and eject smaller objects into space, a cosmic chaos that sculpts the architecture of a star system. Our own solar system's early history bears witness to this violence. The colossal impact believed to have formed our moon, for example, likely involved a Mars-sized body colliding with the nascent Earth, dispersing debris that eventually coalesced into our natural satellite. Similarly, other star systems undergo violent epochs where large bodies break apart, scattering fragments far and wide. Another mechanism capable of ejecting debris involves close encounters between star systems. When two stellar systems pass near each other within the galaxy, gravitational interactions, sometimes quite intense, can fling objects from their original orbits, sending them on interstellar trajectories that carry them across vast distances. Computer simulations suggest that such stellar flybys are not rare over galactic timescales. They occur regularly enough to produce a continuous influx of interstellar wanderers drifting through space, some of which may eventually cross paths with our solar system. Even more dramatic are the consequences of planetary or moon destruction. Catastrophic breakup events, whether caused by intense tidal forces during a close approach to another star, internal instabilities such as runaway greenhouse effects, or even advanced technological disasters, potentially a form of planetary-scale catastrophe, would generate vast shells of debris. These shells, traveling at high velocities, could expand and disperse throughout interstellar space, forming expansive clouds or fields of fragments that drift across the galaxy. Over time, these debris fields can become dispersed, their constituent parts traveling independently, yet still sharing a common origin. In considering these processes, the chemical and physical characteristics of debris fields become relevant. For instance, a debris fragment originating in a cold outer region of a star system's protoplanetary disk could contain high concentrations of volatile compounds like carbon dioxide ice, materials that remain stable under low-temperature conditions over eons. If such fragments were ejected during a violent event, their chemical signatures would carry the imprint of their cold, distant birthplace. Over millions of years, cosmic rays and other space-weathering processes could modify their surface properties, imparting distinctive reddish spectral slopes or polarization signatures, clues that might help identify their origins. The debris field hypothesis therefore offers a plausible natural explanation for objects like 3IATLAS. It suggests that rather than being an anomaly of extraterrestrial craftsmanship, this comet could be a relic of ancient cosmic violence, an interstellar messenger bearing silent testimony to the violent history of distant star systems. This perspective does not dismiss the possibility of artificial origins, but emphasizes that many of the peculiar features observed, such as unusual chemistry, rapid activity, and the distinctive chemical makeup of 3IATLAS, particularly its abundance of carbon dioxide, offers intriguing clues about its origins. This particular composition hints at formation in the frigid outer reaches of another star system, where temperatures are low enough to allow carbon dioxide ice to remain stable over vast geological timescales. Such conditions are plausible in the debris disks surrounding stars that have undergone violent upheavals. Catastrophic events that eject material into interstellar space before it can be subjected to the intense heating and thermal processing typical of standard planetary formation. Furthermore, some analyses have revealed a reddish spectral slope in the light reflected from 3IATLAS, suggesting a complex and unusual history. This coloration could be a result of prolonged exposure to cosmic rays during an extended voyage through the depths of interstellar space. Over countless millennia, cosmic radiation can alter the surface chemistry and physical properties of spacefaring material, imparting a distinctive reddish hue. Alternatively, this hue might mirror the original composition of the material that coalesced under conditions markedly different from those that formed objects within our solar system. Conditions that fostered different chemical pathways or preserved different volatile compounds. Such a reddish tint is reminiscent of objects in the distant outer regions of our own solar system, such as certain trans-Neptunian objects that have been heavily modified by eons of radiation exposure, giving them their characteristic coloration. The anomalies in polarization observed in previous analyses lend further support to the debris field hypothesis. If 3IATLAS is composed of material that experienced a different formation process or was subjected to unique environmental conditions during its interstellar journey, then the dust grains it contains would likely possess optical properties unlike anything observed in our local cosmic neighborhood. These exotic dust textures could originate from shock processing, an intense heating and alteration phase caused by a catastrophic ejection event, such as a collision or violent disruption of a parent body. Alternatively, they might have gradually evolved through continual modification by interstellar radiation over millions of years, resulting in unusual surface textures and optical signatures. It's important to note, however, that the apparent clustering of multiple unusual objects in our sky during this period does not necessarily prove a common origin. The seeming coincidence might simply be a consequence of observational bias. With advances in detection technology, astronomers now identify and monitor faint distant objects more effectively than they could even a decade ago. This heightened sensitivity and improved capability to detect subtle phenomena could reveal a multitude of interstellar visitors that would previously have gone unnoticed, creating an illusion of a synchronized arrival. Adding to this the heightened solar activity expected in the year 2025, the solar maximum, may also influence the visibility of such objects. During periods of intense solar activity, the interaction between the solar wind and a comet's atmosphere often becomes more dramatic. These interactions can enhance the comet's brightness or produce distinctive phenomena, rendering borderline objects more conspicuous and newsworthy than they would appear during calmer solar periods. Such conditions could temporarily amplify the visibility of faint interstellar debris, skewing the apparent frequency of such events. If 3IATLAS is indeed part of a larger debris field resulting from an ancient catastrophic stellar event, then future years may reveal additional interstellar objects passing through our solar system. The upcoming Vera Rubin Observatory's Legacy Survey of Space and Time is poised to dramatically expand our detection capabilities. Its unprecedented sensitivity to faint, fast-moving objects will likely uncover a hidden population of interstellar visitors, cosmic remnants that have silently traversed the galaxy, unnoticed until now. The concept of a dispersed debris field becomes even more plausible when considering how such material, ejected during a violent event, would evolve over time. Imagine debris ejected from a catastrophic explosion, comparable to confetti released from a moving vehicle. Initially, this material would be tightly clustered, traveling together in a relatively concentrated group. But over thousands or even millions of years, gravitational interactions with stars, interstellar clouds, and the subtle tug of galactic tides would gradually disperse this debris across an ever-expanding volume of space. This gradual spreading would ensure that remnants of a single ancient event could arrive at our solar neighborhood in scattered waves, providing a natural explanation for the sporadic appearance of interstellar objects like 3IATLAS. From our vantage point on Earth, the prospect of identifying remnants from such a distant and ancient cosmic catastrophe is akin to trying to piece together a shattered firework explosion from thousands of miles away, long after the initial burst has faded into history. Imagine, if you will, fragments of debris arriving at different times from slightly varying directions, complicating the task of recognizing any shared origin without the aid of detailed analyses. Without precise knowledge of their composition and the trajectories they follow through space, these fragments would appear as a scattered, unconnected collection rather than a coherent field stemming from a single cataclysmic event. So what kind of evidence would bolster the debris field hypothesis? The idea that these fragments originated from a massive, ancient cosmic disaster. The strongest support would come from shared signatures in their chemical makeup. If multiple interstellar objects exhibit similar compositional fingerprints, specific ratios of elements and molecules that significantly differ from those found in our solar system's native materials, it would imply a common extraterrestrial source. Such distinctive signatures could include unusual isotopic ratios or unique organic compounds that are unlikely to occur naturally within our local celestial neighborhood. Equally compelling would be the discovery of comparable dynamical properties among these fragments. For instance, if their velocities and orbital trajectories, how they move and travel through space, are sufficiently similar to be traced back to a single point in the galaxy, it would suggest they are remnants of a shared origin. These objects, despite having drifted across the universe over millennia, could be identified as fragments of a once cohesive debris cloud resulting from a catastrophic event. To test this idea rigorously, scientists could employ sophisticated computer simulations that model how debris disperses after such a cosmic catastrophe. By inputting parameters of various hypothetical events, like planetary collisions, stellar explosions, or large-scale fragmentation, researchers could generate predicted patterns of arrival times and compositional distributions. If the simulations produce results that align with what we currently observe, showing similar dispersal timelines and material signatures, it would lend significant credibility to the debris field hypothesis. Considering the enormous timescales involved, the story becomes even more extraordinary. Suppose that the interstellar object known as 3IATLAS originated from a debris-producing event that took place 10,000 years ago in a star system 50 light-years away. In that case, this object would have been journeying through the cold depths of interstellar space long before humans even began to develop agriculture. The catastrophe that generated this debris might have occurred when our earliest ancestors were still roaming as hunter-gatherers, completely oblivious to the cosmic violence scattering remnants across the galaxy. Over the course of millennia, these fragments have been drifting silently through the void, eventually reaching our solar system. An astonishing reminder of the galaxy's violent and chaotic history. From a broader perspective, the debris field hypothesis offers a balanced middle ground between the more exotic idea of alien technology and the simplest natural explanations. It does not require any violation of the known laws of physics, nor does it presume the existence of highly advanced extraterrestrial machinery. It also avoids the conspiracy theories that posit secret government knowledge or hidden agendas. Instead, it invites us to accept that the galaxy might be a far more tumultuous and turbulent environment than the relative tranquility of our solar system suggests. Cosmic collisions, stellar upheavals, and planetary disintegrations could all be common, scattering debris across the interstellar medium in patterns that occasionally intersect with our own. The implications of this idea extend well beyond the case of 3IATLAS. If interstellar debris fields are indeed commonplace, they could serve as natural laboratories, cosmic archives, preserving the conditions and materials of ancient planetary systems. Each fragment, each piece of debris would carry within it chemical clues about the environment in which it formed, the temperature, the composition, the planetary processes that once shaped its original home. Studying these fragments would offer invaluable insights into stellar evolution, planetary formation, and the broader history of our galaxy, information that we could not access through direct observation of distant systems alone. But the debris field hypothesis is not the only game in town. What if instead 3IATLAS and its companions are not merely accidental fragments from some cosmic disaster, but are instead deliberate scouts, interstellar emissaries dispatched by an intelligent civilization? These explorers might regard our solar system as territory worth investigating, sending out probes to gather information, assess potential resources, or monitor emerging technological civilizations. This leads us to the intriguing scout theory, first proposed in the early 1960s by mathematician and astrophysicist Ronald Bracewell. His concept has since become a foundational idea haunting the search for extraterrestrial intelligence. Bracewell suggested that instead of broadcasting signals across the vast, noisy corridors of space, advanced civilizations could deploy autonomous, self-guided probes, small, durable, and capable of long journeys, to explore neighboring star systems. These probes would act as galactic messengers, gathering detailed data about planets, atmospheres, and potentially even life forms, all while remaining stealthy and undetectable. The reasoning behind Bracewell building upon the pioneering ideas of Frank Bracewell, who proposed that advanced civilizations might opt to send autonomous messenger probes rather than relying solely on broadcasted radio signals across the vast expanses of interstellar space. A compelling case emerges for considering such probes as a means of galactic exploration. These hypothetical scouts would be vastly more effective than electromagnetic signals for acquiring detailed information about distant star systems and their inhabitants. From an engineering standpoint, the logic of deploying physical probes is persuasive. Radio waves diminish in strength according to the inverse square law. meaning that as the distance increases, the signals become exponentially weaker and harder to detect or decode. In contrast, a physical vessel traveling directly to a target system could utilize onboard sensors and sophisticated instruments to conduct comprehensive surveys, something impossible to achieve remotely from light years away. Expanding on Bracewell's concept, the renowned mathematician John von Neumann had earlier envisioned the existence of self-replicating machines, probes capable of constructing exact copies of themselves using the local materials available in their environment. When combined with the idea of autonomous scout probes, these self-replicating systems, often called von Neumann probes, offer a mechanism for a galaxy-wide deployment. Each probe, upon reaching a suitable star system, could manufacture additional copies, setting off a cascade of replication that would allow such a network to expand exponentially over cosmic timescales. Over millions of years, this process could theoretically result in a broad surveillance grid, with countless probes systematically exploring and monitoring star systems throughout the galaxy. Applying this scout theory to the interstellar object known as 3IATLAS invites us to entertain the possibility that this visitor might in fact be a product of such a reconnaissance network. Instead of revealing its artificial origin through overt technological signatures, like radio emissions or detectable propulsion, an advanced probe could be designed to masquerade as a natural celestial body, such as a comet, in order to remain undetected. From a stealth perspective, this strategy would be remarkably effective. Natural comets are common and follow predictable orbital paths governed by gravity, making them ideal cover objects. A probe embedded within or mimicking a comet could traverse the inner solar system, conducting detailed observations of planets and other celestial bodies while remaining indistinguishable from a natural visitor. The trajectory of 3IATLAS, for instance, appears to carry it past Mars, presenting a tantalizing opportunity to study that planet's atmosphere and surface, possibly through instruments designed to operate during its close approach, before continuing inward for subsequent observations of Earth and Venus. The timing of such an arrival could be strategically significant. If the purpose of the probe's mission was to assess the technological capabilities of civilizations like ours, arriving during a period of heightened solar activity, such as the current solar maximum, might be intentional. Solar maximum conditions, characterized by increased solar wind and space weather events, could be used to observe how our technological infrastructure responds to space-induced stresses, including satellite communications, power grids, and other critical systems. Furthermore, the unusual patterns of brightness observed in 3IATLAS might serve purposes beyond mere natural outgassing. If this object were indeed a highly advanced probe, it could have been equipped with sensors, communication devices, and other systems that deliberately modulate its apparent brightness. Controlled variations in its luminosity, for example, could function as signals, either as a form of data transmission, system testing, or both, disguised as natural phenomena. The rapid expansion of its coma might not be solely due to natural sublimation of ices, but could result from the deliberate deployment of sensor arrays or communication antennas cleverly concealed within the comet-like envelope, designed to mimic natural outgassing while actually serving as a sophisticated signaling system. The chemistry of 3IATLAS also warrants careful consideration. Its apparent abundance of carbon dioxide, which is atypical for a comet from our solar system, could be a deliberate choice. Perhaps a material optimized for certain functions, such as efficient gas production or thermal regulation, rather than a mere byproduct of formation. This chemical signature, combined with other peculiarities, suggests that we might be observing a probe engineered for a specific purpose. Perhaps to operate effectively in the harsh environment of interstellar space while remaining undetectable or indistinguishable from a natural celestial object. Utilizing carbon dioxide as both a propellant and a form of optical camouflage presents a compelling strategy for an interstellar probe designed to operate covertly while maintaining the illusion of natural cometary activity. Such a craft could make precise, subtle course adjustments, all the while adhering to trajectories governed solely by gravity, thus avoiding detectable propulsion signatures. The peculiar anti-tail configuration observed in objects like 3IATLAS could, in this context, serve a dual purpose. From a natural perspective, it might be explainable through perspective effects related to viewing angles. But in a designed system, it could also be intentionally oriented to optimize energy collection from the sun. By angling its solar panels to maximize power intake, an artificial object could enhance its operational efficiency while simultaneously generating visual phenomena, such as a green fluorescing coma, that reinforce its comet-like appearance. Of particular interest are the extreme polarization signatures detected from such an object, which stand out as perhaps the most intriguing evidence supporting a scout or artificial hypothesis. Natural cosmic dust grains under known physical conditions have never been observed to produce polarization effects of the magnitude or character seen in 3IATLAS. This suggests that the dust particles or material coatings on a hypothetical probe might be engineered with exotic optical properties, tailored for specific electronic or optical functions, properties that would be impossible to find in natural interstellar dust. From a materials science perspective, the construction of such a probe would require advanced protection against the harsh environment of interstellar space. Shielding from cosmic rays, impacts from interstellar dust particles, and extreme temperature variations encountered during its long voyage between stars. To withstand these conditions, the craft might employ innovative composite materials or unique coatings, exotic substances with optical and structural characteristics unlike anything in natural cosmic material inventories. The small size of the probe's core, its nucleus, favors the scout hypothesis, as a highly capable yet compact system could house sophisticated sensors, communication hardware, and energy collection systems within a scale of only a few kilometers, consistent with the observed dimensions of 3IATLAS. Modern miniaturization technologies already enable the packing of high-performance instruments into tiny packages, and an advanced civilization might push these capabilities even further, compressing extensive functionality into a small, stealthy form factor. Yet this scout hypothesis encounters significant empirical hurdles. Extensive monitoring efforts, including worldwide radio telescopes, have yet to detect any confirmed artificial signals emanating from 3IATLAS. Furthermore, the object shows no clear evidence of active control, no course corrections or maneuvers suggestive of an engineered guidance system, its trajectory remaining consistent with purely gravitational influences within the solar system's dynamics. The formidable engineering requirements for a true interstellar reconnaissance probe are staggering. Such a craft would need to endure thousands of years traversing the radiation-rich environment of interstellar space, maintaining its operational systems intact across such extended durations. It would also need to execute complex scientific or observational objectives upon arriving at its target, demanding a level of technological sophistication that far exceeds current human capabilities. If such probes do indeed exist, their creators would likely possess technology vastly more advanced than ours, advanced enough to have already detected our own radio emissions and other technological signatures from their home star system. In essence, while the concept of an artificially constructed camouflaged interstellar scout aligns with some of the unusual signatures observed from 3IATLAS, such as its peculiar polarization and rapid activity, current observational evidence remains inconclusive. The absence of detectable signals, guidance maneuvers, or other clear hallmarks of artificial origin poses a significant challenge to the hypothesis. Nonetheless, the extraordinary properties observed continue to fuel speculation, about whether we might be witnessing a highly sophisticated covert technological artifact from an alien civilization, one designed to blend seamlessly into the natural cosmic environment, yet capable of performing long-range reconnaissance undetected. The notion that a highly sophisticated civilization would need to deploy close-up reconnaissance seems increasingly unnecessary, especially given the advanced capabilities that such entities might possess. When considering the idea of extraterrestrial explorers, the concept of a scout mission naturally invites questions about motivation and timing. Why would an intelligent species choose this precise moment in human history to send out probes to observe us? Our technological signatures, radio broadcasts, satellite signals, and other detectable emissions have only been observable for less than 100 years, a fleeting blink in the vast expanse of cosmic time. This brief window of visibility makes it seem almost too convenient that these potential visitors would arrive now, during humanity's early technological adolescence. The coincidence of the arrival of such a probe, like the mysterious object known as 3IATLAS, during this particular era of human development appears remarkably serendipitous. Yet this combination of unusual characteristics and perfectly timed appearance weaves a compelling narrative that fuels speculation. If one were to design an interstellar reconnaissance mission, many of the observed features could be perfectly justified from an engineering standpoint. The probe might be gathering detailed data about Earth's atmosphere, magnetic field, or even our technological infrastructure, while outwardly appearing to be just another natural celestial object or comet. Its trajectory could be optimized to provide a broad survey of multiple planets and environments, making the most of the immense resources required to travel between stars. Most intriguingly, if 3IATLAS indeed represents a scout from an advanced civilization, it might not be operating in isolation. The apparent cluster of peculiar objects and anomalies in our sky could be part of a coordinated reconnaissance effort with multiple probes conducting simultaneous observations from different vantage points across our solar system. This raises perhaps the most profound question of all. If the galaxy hosts civilizations capable of launching interstellar missions, why have we not encountered definitive evidence of their existence until now? This dilemma echoes one of the most famous puzzles in science and philosophy, what is known as the Fermi paradox. Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" during a casual lunch at Los Alamos in the year 1950. The question underscores a profound contradiction. On the one hand, the universe appears ripe for life. The sheer number of stars and planets suggests that extraterrestrial civilizations should be common. On the other hand, despite the high probability, there remains a conspicuous silence. No clear signs, no confirmed encounters, and no undeniable evidence of other intelligent life forms. Fermi's simple yet profound question has since been formalized into what we now call the Drake equation, developed by astronomer Frank Drake in the early 1960s. This mathematical framework attempts to estimate the number of technologically capable civilizations in our galaxy by multiplying various factors: the rate of star formation, the fraction of stars with planets, the number of habitable worlds per planetary system, and the probability that life, once formed, develops intelligence and technological capabilities. Even when applying conservative estimates within this model, the numbers suggest that our galaxy should be teeming with thousands, if not millions, of intelligent societies capable of communication or exploration. Considering that our Milky Way galaxy contains around 400 billion stars, and that billions of years have elapsed since its formation, the apparent absence of obvious alien visitors or signals becomes even more perplexing. The statistical odds based on current understanding imply that extraterrestrial civilizations should be relatively widespread, yet we find ourselves in a silent cosmos. This stark discrepancy, the core of the Fermi paradox, continues to challenge our assumptions about life beyond Earth and remains one of the most intriguing mysteries in science today. Interstellar objects such as 3IATLAS offer invaluable new insights that help refine and expand several parameters within the framework of the Drake equation, which estimates the number of technologically advanced civilizations in our galaxy. The recent discovery of thousands of exoplanets around distant stars has unequivocally demonstrated that planetary formation is a common and perhaps even inevitable outcome of stellar evolution. This widespread occurrence directly informs the factor in the Drake equation that estimates the fraction of stars in the galaxy that host planetary systems, indicating that such systems are not rare anomalies but rather a typical feature of star formation. Furthermore, the detection of comets and asteroids that have been ejected from other star systems provides compelling evidence that planetary system formation involves violent and tumultuous processes. These events, such as gravitational interactions, planetary migrations, and catastrophic collisions, scatter debris across the vast expanses of interstellar space. Each fragment of this debris traveling through the galaxy serves as a chemical and physical record of its origin, carrying signatures that can reveal the composition of the parent star system, the nature of planetary formation, and the prevalence of conditions conducive to habitability elsewhere in the universe. Specifically, every interstellar comet acts as a cosmic messenger, bearing the chemical fingerprints of its birthplace. Analyses of their atmospheres and dust compositions can potentially unveil detailed information about stellar makeup, such as elemental abundances, and the processes that lead to planet formation within those systems. For example, the carbon dioxide-rich chemistry observed in 3IATLAS might suggest that it formed in the colder outer regions of its original system, where temperatures are sufficiently low to allow stable ice of volatile compounds like carbon dioxide over billions of years. Such environments are believed to be common in the debris disks surrounding many stars, implying that the building blocks for life, organic molecules and volatile compounds, might be widely distributed throughout the galaxy. From an astrobiological perspective, this widespread distribution of life's fundamental ingredients enhances the possibility that habitable environments could be more prevalent than previously assumed. If advanced civilizations exist elsewhere, they might use interstellar objects as covert tools for reconnaissance, disguising their probes or observational devices within natural debris. During periods when multiple comets and asteroids happen to be visible from Earth, these artificial visitors could blend seamlessly into the background of genuine celestial phenomena, making detection exceedingly difficult. This strategy of using natural cosmic clutter as camouflage might offer an elegant solution to the long-standing Fermi paradox. The question of why, despite the vast number of stars and planets, evidence of extraterrestrial intelligence remains elusive. One plausible resolution is that extraterrestrial visitors are already present within our solar system, but are employing highly sophisticated, low-profile methods to observe and gather data without revealing their presence. Rather than making overt displays of technology or signaling intent, they might prefer subtle, indirect reconnaissance, collecting information quietly, avoiding triggering the natural human responses of alarm or suspicion. The scout theory posits that civilizations capable of interstellar travel are likely rare but not non-existent. Even with low probabilities for the development of life, intelligence, and technological capability, the sheer scale and age of the galaxy mean that occasional interstellar reconnaissance missions could occur. These missions might be conducted by craft or objects that resemble natural debris, thereby avoiding detection or suspicion. This also means that the clustering of multiple interstellar objects, such as the current autumn comet swarm, could be coincidental, resulting from natural dynamical processes rather than coordinated activity by an intelligent civilization. Nonetheless, natural explanations for the unusual properties observed in 3I₄ remain highly plausible and perhaps even more likely than artificial origins. Its volatile composition, rapid expansion of its coma, and extreme polarization properties could all be the result of natural processes, perhaps involving an exotic formation history, or an internal structure shaped by a unique evolutionary pathway. The apparent clustering of comets and asteroids in our skies during the fall of 2025 might simply reflect advancements in detection technology, allowing us to observe phenomena that previously went unnoticed, combined with natural gravitational and dynamical forces that periodically send multiple objects on similar inward trajectories. In essence, these observations could be the natural consequence of the galaxy's dynamic and chaotic environment, where violent events scatter debris and improved observational capabilities reveal these phenomena more clearly than ever before. Such a perspective underscores that what may appear as extraordinary or seemingly orchestrated may, in fact, be the natural and inevitable result of the complex gravitational choreography and chemical evolution shaping planetary systems across the cosmos. In our rapidly evolving understanding of the cosmos, technological advancements have significantly enhanced our capacity to detect and monitor faint, previously hidden phenomena within our solar system. This heightened sensitivity means that events once thought to be beyond our observational reach are now emerging into clarity, inviting new questions and challenging our assumptions. The scientific method, a cornerstone of rational inquiry, mandates that we thoroughly explore all natural explanations before considering extraordinary or speculative ideas. This approach aligns with the principle of Occam's razor, which advises us that among competing hypotheses, the simplest one, requiring the fewest assumptions, is usually the most plausible. When faced with unusual phenomena, the default stance is to extend our current understanding of known physics, recognizing that many natural anomalies can be explained by subtle variations or extensions of established scientific principles. Conversely, hypotheses proposing artificial origins, such as the intervention of advanced extraterrestrial technology, demand extraordinary evidence, primarily because they imply the existence of highly sophisticated civilizations capable of interstellar travel and reconnaissance. Such propositions are inherently more speculative, requiring us to posit the existence of technology far beyond our current capabilities. Yet, despite the cautious skepticism encouraged by Occam's razor, we cannot entirely dismiss the possibility that some anomalies may be the product of alien engineering. If interstellar reconnaissance probes do exist, their design and operational requirements would likely align with many of the characteristics observed in objects like 3IATLAS. These probes, conceived for long-duration missions, would need to be built with simplicity and durability in mind, capable of surviving thousands of years traveling through the cold, harsh environment of interstellar space. Their systems would favor minimal complexity, robust, reliable, and capable of autonomous operation over extended periods. To maintain stealth and avoid detection, such probes would probably be engineered to imitate natural phenomena. They might mimic the appearance of comets or asteroids while secretly conducting scientific observations. Their timing and trajectories could be deliberately chosen to blend seamlessly into the cosmic background, making their artificial nature difficult to discern from Earth-based or space-based observation points. However, a fundamental challenge to the Scout hypothesis concerns the timing of these potential missions. Why would an advanced extraterrestrial civilization choose precisely this moment in human history? An era characterized by a mere century of detectable radio emissions and a few decades of space infrastructure to dispatch reconnaissance probes. The coincidence of such arrivals occurring during our so-called technological adolescence appears remarkably fortuitous raising suspicions about intentionality or deliberate timing. One plausible explanation is that such reconnaissance missions are not initiated in response to specific technological milestones, but are part of routine surveys, ongoing efforts by advanced civilizations to monitor nearby star systems at regular intervals. If this is the case, the arrival of probes would follow statistical patterns, independent of the developmental stage of the civilization being observed. In this scenario, the timing would be a matter of coincidence, governed by the natural distribution of interstellar objects and survey patterns. Alternatively, our technological signatures, such as radio communications, satellite emissions, or other electromagnetic signals, might be more detectable by extraterrestrial observers than we typically assume. High-energy activities like nuclear tests, powerful radar transmissions, or widespread satellite communications could be visible across vast interstellar distances, serving as beacons that draw attention to our presence. In this light, objects like 3IATLAS could simply be responses to decades of increasingly detectable technological activity, serving as a form of galactic reconnaissance. Traditionally, the search for extraterrestrial intelligence has concentrated on electromagnetic signals, radio waves, laser pulses, or other forms of communication. But recent considerations suggest that physical visitors, artificial probes, might be far more common than we have imagined. Civilizations seeking to gather information directly rather than risking detection through long-range signals might prefer deploying autonomous craft to observe and analyze distant worlds firsthand. Given this, our focus on electromagnetic detection could be missing a significant part of the picture. Future observations of interstellar objects like 3IATLAS will be crucial in resolving these questions. If such objects are ultimately shown to be natural, their exotic properties, such as unusual compositions or behaviors, would broaden our understanding of planetary formation, chemical evolution, and physical processes in other star systems. Conversely, if evidence accumulates pointing to artificial origins, it would represent a revolutionary breakthrough, confirming that intelligent civilizations not only exist beyond Earth but are actively exploring the galaxy. In essence, the true nature of objects like 3IATLAS remains an open question, one that sits at the intersection of scientific curiosity, technological possibility, and the profound mystery of whether we are alone in the universe. The deepest and most far-reaching consequence of the Fermi paradox may lie in the idea that highly advanced civilizations exist within our galaxy, yet they remain extremely subtle in their presence. These civilizations might operate using highly sophisticated methods of observation and communication, techniques so refined that their activities evade easy detection, all while they quietly gather vital information about their surroundings. From this vantage point, the interstellar object known as 3IATLAS could very well be our first tangible glimpse of galactic civilization in motion. However, whether we are simply observing natural cosmic phenomena or encountering something far more extraordinary, the implications are staggering and profound. On one hand, the universe might be far more violent, unpredictable, and chaotic than our current understanding of the solar system's relative stability suggests. On the other hand, we could be witnessing undeniable evidence of intelligence functioning on scales so vast and advanced that they surpass human comprehension. This dichotomy between the natural and the potentially artificial sets the stage for a debate that has gained momentum in recent years, challenging long-held assumptions about our place in the cosmos. As 3IATLAS continues its inexorable journey toward the inner reaches of our solar system, the scientific community finds itself embroiled in discussions that would have once been considered the realm of science fiction. The accumulating evidence, though far from definitive, has become compelling enough that serious researchers are now openly exploring possibilities that extend well beyond traditional astronomical explanations. On one side of this debate are astronomers with decades of experience studying comets and asteroids, whose interpretations favor natural origins. They argue that the unusual brightening observed in the comet results from interactions involving exotic volatile compounds, substances that behave differently under solar heating than those typically found in our solar system, thus fitting into a framework of natural processes that we are still striving to fully understand. Furthermore, the peculiar anti-tail geometry, which at first glance appears to defy the norms of comet behavior, can be explained through viewing angle effects combined with complex dust distribution patterns surrounding the object. The extreme polarization characteristics observed in the comet's coma, indicating dust grain properties that differ from familiar solar system materials, are interpreted by these scientists as evidence of natural phenomena, albeit with some exotic variations. They emphasize a fundamental scientific principle, that extraordinary claims demand extraordinary evidence. While 3IATLAS exhibits properties that are indeed unusual, none of its characteristics conclusively negate the possibility of a natural origin. The comet's high carbon dioxide content, rapid expansion of its atmosphere, and peculiar polarization signals could all plausibly result from formation conditions in an entirely different star system, where environmental factors and chemical evolution diverge significantly from those on Earth or within our local cosmic neighborhood. Conversely, an increasing number of voices, some motivated by skepticism, others by curiosity, point to the pattern of anomalies and coincidental timing in autumn 2025 as suggestive of something more than mere chance. The collective appearance of multiple bright comets and a wave of asteroid close approaches during this period creates an impression of deliberate coordination that is difficult to attribute solely to randomness. The striking green fluorescence, the almost unnatural anti-tail geometry, and the rapid growth of the coma all contribute to a visual spectacle that seems almost engineered or designed to attract attention. From this perspective, the timing and appearance of these events are viewed with suspicion, prompting questions about whether they might be orchestrated signals or demonstrations, perhaps even deliberate probes, by an unseen intelligence. The conspiracy-minded interpretation emphasizes the coincidence of multiple unusual objects arriving in our vicinity within a narrowly defined window. Why would so many interstellar visitors appear simultaneously, exhibiting such strange behaviors, unless their appearances were somehow coordinated by an external force? The convergence of mid-September asteroid activity, the peculiar characteristics of 3IATLAS, and the striking visual features collectively form a narrative framework that naturally lends itself to speculation about external orchestration, implying that some intelligent agency might be actively observing, testing, or even communicating with us through these celestial phenomena. It is essential to underscore, however, that 3IATLAS poses no immediate threat to Earth, regardless of whether it is a natural or an artificial object. Its closest passage to our planet is expected to occur on December 19th, at a distance of approximately 1.8 astronomical units, roughly 170 million kilometers away. In cosmic terms, this is a safe margin. It places the comet well beyond the orbit of Earth's own trajectory, ensuring that a collision or impact scenario is entirely out of the question. Throughout its journey through the inner solar system, the comet's path will take it past several celestial bodies, Mars, Venus, and Jupiter, each at distances measured in millions of kilometers. While these encounters may seem relatively close in astronomical terms, they are still separated by vast expanses of space, making any direct interaction with these planets unlikely. Even if, hypothetically, 3IATLAS were to be controlled by an artificial intelligence or extraterrestrial agency, its current course and velocity do not provide any plausible mechanism for threatening Earth or any other planet in the system. The allure of such exotic explanations becomes especially compelling when considering the spectacular visual phenomena that the comet exhibits. Its vivid green glow, the peculiar anti-tail geometry, and the swift increase in brightness evoke imagery often associated with science fiction narratives. Images of alien craft or otherworldly entities. Our cultural conditioning predisposes us to interpret striking astronomical events through a lens of the extraordinary, frequently imagining scenarios involving advanced extraterrestrial technology. Popular culture has long shaped expectations that contact with alien civilizations would manifest through dramatic displays. Obvious signals, conspicuous technological signatures, or unmistakable signs of artificial origin. Such portrayals naturally influence public perception, leading many to see these phenomena as potential evidence of intelligent intervention. Yet the reality underlying these striking visuals could be far more subtle and nuanced. Conceivably, what we observe might be the result of reconnaissance missions deliberately designed to remain undetectable, aimed at gathering information without provoking a defensive response from a primitive civilization like our own. From this perspective, the very debate surrounding the nature of 3IATLAS might be an intentional consequence of such covert operations, an orchestrated form of observation that fuels scientific curiosity and public discussion, while avoiding the kind of definitive proof that could trigger panic or prompt drastic policy responses. This strategic ambiguity allows ongoing observation and analysis, ensuring that the investigation continues unimpeded, while sidestepping the societal upheaval that unambiguous alien contact might provoke. The central issue of timing remains pivotal in evaluating the various interpretations. Proponents of natural explanations argue that our improved detection technologies and the heightened interest in space phenomena have created a bias, making routine or insignificant events appear more extraordinary than they truly are. They contend that our enhanced observational capabilities simply mean we are now better at discovering and publicizing unusual objects, a development that has occurred over recent decades. Conversely, supporters of the exotic hypothesis suggest that the clustering of these phenomena, multiple bright comets and a wave of close-approaching asteroids within a short period, surpasses what random chance would statistically predict, especially considering how rare interstellar visitors are and the relatively brief history of systematic sky surveys capable of detecting them. The coincidence of several unusual celestial events unfolding during humanity's comparatively young era of technological development seems to demand an explanation that extends beyond mere luck or natural variability. Most astronomers working on the case of 3IATLAS tend to maintain a cautious public stance of neutrality. They acknowledge that the object's behavior and characteristics are pushing the limits of current scientific understanding. Privately, many experts admit that what they are witnessing is extraordinary, challenging existing models and prompting ongoing debate about the true nature of this cosmic visitor. While they refrain from jumping to sensational conclusions, their private assessments reflect a recognition that the phenomena observed could signify either a natural object with highly unusual properties or something more enigmatic, possibly artificial in origin. The data on polarization in particular stands out as a set of measurements that do not align with any previously recorded natural objects. Such a discrepancy demands either a significant expansion of our current scientific theories, pushing the boundaries of what we understand about space phenomena, or an openness to considering more extraordinary, perhaps even exotic explanations. The response from the scientific and institutional community has been notably cautious. Leading observatories and space agencies have concentrated primarily on analyzing the technical aspects of the observations, deliberately steering clear of making speculative claims or drawing bold implications. This conservative stance is rooted in both the rigorous principles of scientific methodology and a pragmatic awareness of how the public might react to interpretations that veer into the sensational or unverified. This cautious approach, while methodologically sound, has inadvertently fostered a growing vacuum of high-resolution data, particularly during the critical month of September, leaving a conspicuous absence of detailed imagery from the most advanced space telescopes. This void has, over time, become fertile ground for conspiracy theories and speculation, as the lack of new information naturally fuels suspicions. While operational constraints, scheduling conflicts, and technical limitations provide straightforward, mundane explanations for the missing images, the timing of this data gap feels suspiciously convenient to those inclined toward more dramatic, perhaps even conspiratorial interpretations. For individuals questioning the transparency or motives behind the silence, it raises a troubling question. If the object known as 3IATLAS genuinely represents something beyond the realm of natural phenomena, how would governments and scientific institutions handle the confirmation of alien reconnaissance? The implications of such a revelation would be profound, touching every aspect of society. It could trigger widespread religious crises, shake the foundations of scientific understanding, destabilize stock markets, and prompt fundamental shifts in international relations and global security policies. Given the gravity of these potential consequences, a gradual, cautious process of disclosure, one rooted in scientific debate and incremental validation, may be the most responsible course of action. Instead of issuing sudden, startling announcements that could induce panic or chaos, this measured approach allows society to adapt slowly, to process the possibility that what we are observing might be a revolutionary discovery that challenges our entire worldview. As 3IATLAS continues its journey toward perihelion in late October, each new observation carries immense significance. Every piece of data has the potential to sway the consensus, either reinforcing the idea that this is a natural, albeit extraordinary comet, or providing evidence of an artificial, possibly engineered object from another star system. The global scientific community is watching with unprecedented intensity, fully aware that this object might challenge or even redefine our understanding of natural phenomena. It could be the first tangible contact with extraterrestrial technology, an event of unparalleled importance. The stakes are extraordinarily high. We might simply be witnessing exotic physical processes playing out in an unusual comet that originated beyond our solar system. Or we could be witnessing the first confirmed signs that humanity is not alone in the galaxy, that other civilizations with the capability and interest are studying us from light years away. Amid this uncertainty, one troubling question has begun to resonate among researchers monitoring the object's progress. Where are the detailed images that we would expect to see from our most powerful space-based telescopes? Part 11 of this ongoing mystery focuses precisely on this issue. Where are the images? A review of the observation timeline reveals an inexplicable gap that has both professional astronomers and conspiracy theorists alike asking uncomfortable, perhaps even provocative questions. While amateur astronomers across the globe continue to post striking photographs showing the comet with its characteristic green-tinged coma and peculiar tail geometry, the most advanced and capable space telescopes have remained conspicuously silent during the crucial month of September. This silence, this absence of high-resolution data from the world's premier observatories, has only intensified speculation about what might be happening behind the scenes in the corridors of science and space agencies. During the critical month of September, the world's leading space-based observatories, those equipped to deliver the highest quality and most detailed data, have fallen remarkably silent, their instruments seemingly going dark at a pivotal moment. The Hubble Space Telescope, which had previously provided invaluable insights into this mysterious object, captured a highly detailed image of 3IATLAS on July 21st. This image revealed the comet's compact nucleus cloaked by a luminous dust cocoon, offering essential constraints on its size and serving as a vital baseline measurement for its unusual characteristics. These initial observations were instrumental in establishing what made 3I₄ so extraordinary, and they drew worldwide attention for their clarity and depth. However, despite the comet's ongoing brightening and the increasingly dramatic spectacle it presented as it approached the inner solar system, no new images from Hubble have been made available to the public since September 22nd. This conspicuous silence raises questions, especially given the continued evolution of the comet's appearance. Meanwhile, the James Webb Space Telescope, renowned for its revolutionary spectroscopic capabilities, had already performed a series of groundbreaking observations on August 6th. These revealed that the comet's composition was heavily dominated by carbon dioxide, and they provided critical insights into its unique chemistry, details that set 3I₄ apart from ordinary comets and hinted at an origin beyond our solar system. These results made headlines across the globe, emphasizing just how fundamentally different this interstellar visitor was. Yet despite the scientific community's intense interest and the wealth of new data, no images or spectroscopic data from JWST have been released for September. Adding to the mystery, the Gemini South Observatory contributed a stunning high-resolution image, capturing intricate details of the comet's complex tail structure. This photograph, which captured the public's imagination with its vivid detail, was taken on August 27th and publicly shared on September 4th. Importantly, this image represents data collected in August, not during the critical September window when the comet was intensifying and exhibiting extraordinary behavior. Under normal circumstances, such a temporal gap in high-quality data would not raise eyebrows. Observatories often operate on complex schedules, with observation slots allocated months or even years in advance based on scientific priorities and technical planning. However, the approaching superior conjunction, when 3I₄ will pass behind the Sun from Earth's perspective, introduces natural limitations on observation opportunities. During this period, the Sun's overwhelming brightness makes direct observations exceedingly difficult or impossible, as most space telescopes cannot safely point too close to the Sun without risking damage to their sensitive instruments. As the comet continues its inward trajectory, these constraints become even more severe, requiring meticulous scheduling, specialized procedures, and careful risk management to protect costly equipment. Furthermore, the system of proprietary periods, an established aspect of professional astronomy, adds another layer of complexity. Research teams who propose observations typically gain exclusive access to their data for a set period, allowing them to analyze and publish results before the broader community can see them. This approach safeguards the significant scientific investment involved and ensures rigorous peer review. Additionally, the process of data calibration and analysis can be time-consuming. Raw data collected by telescopes must undergo extensive processing, verification, and interpretation before it can be shared publicly. For complex observations, this entire pipeline can take weeks or even months, delaying the release of high-resolution images and detailed findings during the most dynamic phase of the comet's approach. The overwhelming demand placed on our planet's most advanced telescopic facilities results in a complex web of logistical limitations. Instruments like the Hubble Space Telescope and the James Webb Space Telescope are inundated with more observation requests than their finite capacities can handle. An oversubscription that forces scientists and mission planners into difficult decisions. Each precious window of observation time must be carefully allocated, often pitting one high-priority target against numerous others deemed equally vital for ongoing research. Consequently, 3I₄, with its extraordinary and perplexing behavior, finds itself vying for limited telescope resources alongside countless other objects that also demand attention. Objects of significant scientific interest, yet constrained by the scarcity of available observation slots. Despite these straightforward operational explanations, many observers find the timing of the conspicuous gap in professional data to be oddly coincidental. September, the very period during which 3IATLAS began displaying its most dramatic and inexplicable phenomena, such as rapid, unexpected brightening that diverged sharply from our established predictive models, and the intensification of a vivid green fluorescence, coincides precisely with the period when access to high-resolution space-based observations became unexpectedly sparse. If government agencies or international scientific alliances had detected truly extraordinary activity in the comet, it would stand to reason that they might impose certain restrictions, perhaps for reasons of national security, classified analysis, or to prevent premature disclosure during this critical phase of its approach. This deliberate withholding or suppression of data, whether motivated by security concerns or other undisclosed reasons, could explain the apparent gap in publicly available information rather than mere operational constraints or scheduling conflicts. Such a scenario raises uncomfortable questions about transparency and the handling of potentially groundbreaking discoveries. Meanwhile, the void in formal scientific data has been filled, at least in part, by a global network of amateur astronomers operating under dark, clear skies in regions such as Namibia, Chile, and Australia. These dedicated observers have captured stunning photographs and detailed visual records of 3IATLAS's evolving appearance throughout September. While their images are invaluable for tracking the comet's changing brightness and the development of its complex tail structures, they lack the spectroscopic detail, precise calibration, and high-resolution imaging that only professional observatories can provide. This creates an unusual and somewhat disjointed information landscape. On one side, social media and online platforms overflow with striking, vividly colored images of the comet's luminous green coma and intricate tail formations. On the other, the authoritative scientific databases remain conspicuously sparse, offering little to no recent high-quality data. This stark contrast underscores the importance of amateur contributions in ongoing monitoring efforts. Networks of skilled amateur astronomers equipped with increasingly sophisticated instruments have provided continuous observations that sometimes surpass the temporal resolution of professional surveys. Their persistent efforts have been crucial in documenting the brightness variations, morphological changes, and overall behavior of 3IATLAS during a critical period of its approach. However, despite the significant role played by these amateur observations, they cannot fully replace the detailed chemical analyses, high-precision astrometry, and calibrated photometric data that space-based telescopes and professional observatories routinely provide. These advanced instruments offer insights into the comet's true nature, its composition, internal structure, and the physical processes driving its unusual activity that remain essential for a comprehensive understanding of this interstellar visitor. The importance of recent professional imagery becomes even more pronounced when viewed in light of the comet's increasingly dramatic appearance. During September, the expectation was that high-resolution observations would have captured the onset of the comet's anomalous brightening, the development of its intensified green fluorescence, and potential alterations in the anti-tail geometry that earlier imagery had documented. Instead, the public record reveals a perplexing gap precisely during the window when the most scientifically interesting developments were unfolding. This absence of data during such a critical phase raises questions about the true reasons behind the withholding of information, whether operational, strategic, or potentially deliberate, adding yet another layer of mystery to the ongoing enigma of 3IATLAS. The timing of these events appears almost deliberately orchestrated to fuel speculation about what might be transpiring behind the scenes within major astronomical observatories and space agencies worldwide. Under normal circumstances, international cooperation in the field of astronomy ensures that significant observational data is shared openly among scientists, promoting transparency and collective understanding. Even when official releases are delayed, preliminary findings, especially those of substantial importance, are typically circulated within the scientific community through confidential channels or pre-publication networks. The conspicuous absence of any leaks or early results from the September observations, despite the extensive global network of professional astronomers and observatories, suggests two possibilities. Either such critical data simply does not exist, or access to it is being carefully restricted and tightly controlled, more so than in previous cases. Looking ahead, the upcoming superior conjunction, the celestial alignment when the comet passes behind the Sun from Earth's vantage point, provides a natural explanation for the anticipated decline in observation opportunities in October. This event makes it exceedingly difficult or even impossible to observe the object directly with Earth-based telescopes, as the Sun's overwhelming glare masks the comet's activity. However, this explanation does not clarify why there was a complete lack of data during September, a period when observational conditions were still favorable. Throughout most of September, the comet remained well positioned in the sky, with sufficient solar elongation to permit safe and effective observations using telescopes on Earth and in space. The fact that no high-resolution images or spectroscopic data emerged during this window raises questions about whether the data was deliberately withheld, or if other technical or strategic reasons are at play. As we move toward the critical date of October 3rd, when multiple spacecraft in orbit around Mars will perform close flybys of the planet, this period represents the final optimal window for obtaining detailed, high-resolution observations of the comet's nucleus and its surrounding coma before the conjunction renders such efforts increasingly challenging. Several spacecraft, designed for planetary and cometary studies, are planning opportunistic observations during this encounter, which could yield invaluable perspectives on the structure and composition of the comet's core and its extending atmosphere. After the conjunction concludes in late October and early November, the comet is expected to gradually reappear in the pre-dawn sky, becoming visible again to terrestrial observers. This reemergence offers a renewed chance for detailed monitoring, which could help scientists assess how the comet's properties have evolved during its perihelion passage, its closest approach to the Sun. The central question remains: will the post-conjunction observations fill the current gaps in information left by the September data blackout? Or was the most critical information already obtained during the earlier period, when access to professional high-resolution data was mysteriously restricted? The scientific community, eager and anxious, awaits these future observations with unprecedented anticipation, fully aware that they could finally provide clarity regarding the true nature of 3IATLAS. Yet the observation void during this pivotal period is only one facet of a broader, more troubling pattern that has led some researchers to question whether the timing of this comet's most dramatic behaviors is entirely coincidental. This brings us to what some might call the conspiracy of timing, the scenario where celestial events align so conveniently that they could be deliberately exploited to obscure or manipulate information. Part 12 of this ongoing discussion emphasizes this point by framing it as a superior conjunction equals a convenient blind spot. The unfolding cosmic choreography in October 2025 has, in the eyes of conspiracy theorists, created what can only be described as a perfect cover-up scenario, while astronomers recognize it as an unfortunate but inevitable observational challenge. During superior conjunction, when 3IATLAS passes behind the Sun from our perspective on Earth, the comet becomes effectively invisible. This alignment occurs when the comet's orbital trajectory carries it to the Sun's far side, placing it on the opposite side of the star relative to Earth. During this period, the Sun's intense brightness and energetic emissions overshadow any signals or activity from the comet, rendering direct observation impossible and creating a temporary blind spot in our survey of the solar system dynamics. As the comet 3I/ATLAS nears its closest approach to the Sun, a critical observational window will almost perfectly align with this proximity. The precise timing of this event is dictated by the fundamental laws of celestial mechanics, rendering it an inevitable consequence rather than a suspicious coincidence. Specifically, October 21st marks both the new moon phase and the moment when the comet reaches its minimum solar elongation, meaning it is positioned at its closest point relative to the Sun from Earth's perspective. During this period, the comet becomes engulfed in the Sun's overwhelming glare, rendering it effectively invisible to ground-based telescopes. Moreover, for spacecraft orbiting in space, observing the comet directly during this time poses significant risks. The intense scattered sunlight and thermal loads threaten the delicate instruments aboard these observatories. Operational teams routinely suspend observations of celestial objects when they approach low solar elongation angles, typically within about 15 to 30 degrees of the Sun, because the danger to the instruments and the degradation of data quality are simply too great. These safety margins are not arbitrary restrictions imposed by bureaucratic procedures but are vital safeguards protecting multi-billion-dollar scientific assets. As the comet draws nearer to the Sun, the brightness of the background sky increases dramatically, and the ratio of the comet's faint signals to the overwhelming solar glare diminishes sharply. Even if it were technically feasible for telescopes to point closer to the Sun, the background brightness would drown out the subtle signals from 3I/ATLAS, making any meaningful data collection nearly impossible. This scenario is akin to trying to photograph a tiny flickering candle flame while staring directly into a powerful searchlight, an endeavor that is fundamentally unfeasible with current technology. From a conspiracy perspective, however, this timing could seem too fortuitous to be mere chance. If certain government agencies or international scientific organizations wish to suppress information about this interstellar visitor during its most active and revealing phase, they could hardly have chosen a better natural cover than the phenomenon of superior conjunction. In essence, the comet will disappear from public view precisely when its most unusual and potentially revealing characteristics are expected to be at their strongest. The period surrounding its perihelion, when comets typically showcase their most spectacular activity, will coincide with this conjunction blackout. On October 29th, 3I/ATLAS is projected to reach its closest approach to the Sun, developing its maximum coma density and an impressive tail, yet remaining hidden from Earth-based observers. By the time it re-emerges from this conjunction in late November, the comet's peak activity will have typically already passed, leaving little observable evidence of its most dramatic phase. It's important to note, however, that a superior conjunction does not lead to a total communication blackout. Multiple spacecraft positioned at various points throughout the solar system are capable of maintaining observation capabilities independent of Earth's line of sight. For example, the Solar and Heliospheric Observatory, known as SOHO, frequently images the region around the Sun and might capture fragments or signals from 3I/ATLAS during parts of its conjunction passage. Similarly, the Solar Terrestrial Relations Observatory, or STEREO, comprises two spacecraft, one ahead of Earth and one behind, providing stereoscopic views of solar activity in the inner heliosphere. These platforms could potentially observe the comet from vantage points that remain clear of the Sun's interference, thus continuing to gather valuable data during the blackout period. The European Space Agency's Solar Orbiter, a pioneering mission designed to study the Sun from high latitudes and close proximity, could offer unprecedented observational vantage points that might prove crucial in unraveling the mysteries surrounding 3I₄atlas. Its elliptical orbit takes it well above and below the plane of the solar system, known as the ecliptic, granting it unique viewing angles that are not accessible to Earth-bound or near-Earth telescopes. During periods when our planet's view of the comet is obstructed, particularly during the upcoming conjunction, Solar Orbiter's perspective could still capture detailed images and data, potentially revealing features of the interstellar visitor that remain hidden from Earth-based observation. In addition to Solar Orbiter's capabilities, several spacecraft orbiting Mars are preparing for a rare and valuable opportunity to observe 3I₄atlas during its close approach to the red planet, scheduled for October 3rd. The high-resolution imaging science experiment aboard the Mars Reconnaissance Orbiter is equipped with advanced imaging tools capable of capturing fine details of the comet's nucleus, tail, and surrounding coma from a vantage point much closer than Earth. The European ExoMars Trace Gas Orbiter, which carries a sophisticated color and stereoscopic surface imaging system, is also poised to gather valuable data on the comet's structure and chemical composition. Meanwhile, the high-resolution stereo camera on Mars Express offers additional imaging capabilities that can provide three-dimensional views of the comet's tail and surface features. These Mars-bound observations are particularly significant because they represent the final window for high-quality imaging before the upcoming conjunction, during which the Sun's glare and the positioning of celestial bodies will render 3I₄atlas largely invisible to Earth-based telescopes and spacecraft. The data collected during this close encounter with Mars will offer crucial insights into the comet's internal structure, its gaseous envelope, and the dynamics of its tail, information that cannot be obtained from ground-based observations due to the limitations imposed by distance and atmospheric interference. The importance of these Mars observations cannot be overstated, as they will likely be among the last opportunities to gather detailed, close-up scientific data before the comet slips behind the Sun's glare. Once the conjunction begins, observational access from Earth and most space telescopes will be severely limited or temporarily impossible. Therefore, the data acquired during the Mars flyby could provide a definitive snapshot of 3I₄atlas's physical and compositional state just prior to its solar perihelion, offering a vital baseline for subsequent analysis. Once the Sun's interference is taken into account, the timing of the re-emergence of 3I₄atlas in late November becomes critical for answering fundamental questions about its true nature. As predicted, the comet is expected to reappear in the pre-dawn skies of both hemispheres, revealing whether it has undergone any dramatic changes during its period of concealment behind the Sun. Should it reappear with an altered brightness, a modified tail structure, or other anomalies, deviations from the typical evolution of a natural comet, such findings would lend weight to the possibility of exotic, perhaps artificial influences at play. Conversely, if it emerges with characteristics consistent with a standard post-perihelion comet, exhibiting predictable dimming, tail behavior, and brightness decline, the natural explanation of a typical comet's life cycle would regain strong support. In essence, the reappearance of 3I₄atlas after its conjunction period will serve as a pivotal moment in this ongoing investigation. It holds the potential to either confirm its status as a naturally evolving celestial body, or to reinforce suspicions that it may harbor unconventional or even artificial features. The coming weeks and months will be decisive, as astronomers and scientists worldwide scrutinize the comet's post-conjunction behavior for clues that could fundamentally alter our understanding of interstellar objects, and perhaps of the universe itself. The approach scheduled for December 19th, although still maintaining a safe distance of approximately 1.8 astronomical units from the Sun, promises to be the most promising window for post-conjunction observations. This carefully calculated timing provides several weeks for the comet to move beyond the intense glare of the sun, making it accessible once more to both ground-based telescopes and spaceborne observatories. In anticipation of this reemergence, amateur astronomy communities across the globe are already mobilizing. Enthusiast groups are establishing coordinated networks and sharing protocols to maximize observational coverage, ensuring that every detail of the comet's return is captured and documented. These grassroots efforts serve an essential role, acting as a vital backup should professional observatories encounter ongoing restrictions or operational challenges that limit data collection during this critical period. The period surrounding conjunction is more than merely a logistical obstacle for astronomers. It transforms into a natural, real-world experiment in the dynamics of information management and transparency. How government agencies, research institutions, and international space organizations handle the inevitable data blackout will reveal much about their priorities, whether they lean toward open scientific inquiry or prioritize secrecy, particularly if the object in question might suggest phenomena beyond standard natural explanations. If 3IATLAS does indeed harbor secrets that transcend current scientific understanding, this conjunction phase could serve as the perfect cover for covert analysis, where results are kept classified and shielded from public view until policymakers decide the appropriate moment to reveal them. The precedent for such clandestine handling of sensitive information is well established in military and intelligence circles, where classified observations and data often remain sealed for years or even decades. In such cases, the transition from mere scientific curiosity to a matter of national security can happen swiftly if the object displays characteristics that prompt concern at the highest levels of government. From an optimistic perspective, however, this period might simply be an unfortunate coincidence, an unavoidable timing issue that temporarily deprives humanity of witnessing what could be one of the most significant astronomical events of our era. The late November emergence of the comet could potentially open new avenues of understanding regarding interstellar visitors and the broader nature of objects originating beyond our solar system. This conjunction then creates a scenario that to some appears ripe for conspiracy theories, conditions that seem almost deliberately engineered to foster ambiguity and debate. Yet at the same time, natural explanations exist that can account for these timing and observational gaps, offering a framework that satisfies scientific skepticism. The timing of the blackout, the inability to acquire high-resolution data during the peak activity phase, and the seemingly orchestrated nature of these events. These elements echo themes often found in science fiction. The situation bears a striking resemblance to a satirical film that warned about scenarios where obvious threats are deliberately ignored or suppressed until it becomes too late to respond effectively, highlighting the potential dangers of information control in the face of unknown phenomena. Part 13. Don't Look Up. The 2021 Netflix film, Don't Look Up, cast a sharp satirical light on humanity's collective response to impending catastrophe, depicting a world where government officials, media personalities, and corporate powers conspire, either consciously or through neglect, to suppress or distort critical information about a colossal comet hurtling toward Earth. The film's darkly comic narrative serves as a mirror, highlighting how societal institutions often prioritize political gain, economic interests, and entertainment over honest communication and urgent action. While Don't Look Up was primarily a biting critique of climate change denial and political dysfunction, the ongoing situation with the interstellar object known as 3IATLAS has starkly echoed many of its themes, creating unsettling parallels that many observant minds find increasingly difficult to dismiss. In the film, astronomers discover a massive comet on a collision course with our planet, a discovery that threatens all life as we know it. Yet despite the gravity of the threat, They encounter relentless obstacles when trying to convey the severity of the impending disaster. Instead of being met with urgent action, their warnings are met with skepticism, distraction, and outright dismissiveness by a bewildered public preoccupied with celebrity gossip, sensational headlines, and political spectacle. Governments, depicted as secretive and self-interested, withhold crucial information, manipulating what is known to manipulate public perception for their own ends. Meanwhile, wealthy tech magnates propose profit-driven solutions, some of which exacerbate the crisis, while mainstream media outlets treat the approaching catastrophe as mere entertainment, sensationalizing or trivializing the threat altogether. The similarities between this fictional scenario and the real-world handling or mishandling of 3IATLAS are striking from the very moment of discovery. The initial detection of the interstellar visitor revealed an object exhibiting a set of characteristics that defy easy explanation, challenging the boundaries of our current scientific understanding. Yet attempts by scientists and astronomers to communicate its significance have been filtered through layers of institutional bureaucracy and media interpretation, often leading to distortion or minimization of the true implications. The film's portrayal of government secrecy and information control resonates eerily with the current observational gaps surrounding 3IATLAS. In Don't Look Up, authorities are depicted as knowing far more about the comet's properties than they publicly acknowledge, conducting secret assessments and withholding information, all while maintaining a facade that everything is under control. However, it's crucial to recognize the key differences that set our reality apart from the fictional narrative. The comet in Don't Look Up posed an existential threat of cataclysmic proportions, an imminent collision with Earth capable of causing mass extinction. Its impact was projected within a matter of months, fueling a climate of urgent panic and desperate attempts at mitigation. Conversely, 3IATLAS is predicted to pass harmlessly at a distance of approximately 1.8 astronomical units, roughly 165 million miles, from Earth on December the 19th. Even the most speculative and exotic hypotheses about its nature do not suggest any imminent threat of impact or planetary destruction. Unlike the fictional comet, which was only discovered a few months before its projected collision, this interstellar visitor has been tracked for over a year, with its trajectory calculated with high precision and confirmed through multiple independent observations. The possibility of collision or impact is effectively non-existent, removing the immediate danger that fuels panic in the fictional scenario. Yet despite the clear absence of threat, the psychological and social dynamics that Don't Look Up portrayed continue to echo in the current public response to 3IATLAS. Social media platforms teem with competing theories and narratives, ranging from straightforward natural explanations to elaborate far-flung conjectures about alien reconnaissance missions. This polarization reflects a broader tension between scientific authority and populist skepticism, a phenomenon the film vividly satirized. The media's sensationalism, which in the film amplified the crisis and turned it into entertainment, finds its counterpart in the real-world coverage of 3IATLAS and the mid-September asteroid encounters. Headlines and social media threads swirl with speculation, confusion, and sometimes outright misinformation, highlighting how difficult it is to convey complex scientific realities to a distracted or distrustful public. The parallels extend even further when considering the manner in which information is managed and disseminated. In Don't Look Up, government officials are depicted as deliberately withholding or manipulating data, conducting clandestine assessments, and downplaying the threat to avoid panic or protect vested interests. Similarly, the current observational gaps, particularly the absence of recent high-resolution data from major space telescopes, have fueled suspicion and conspiracy theories. Official statements emphasize operational constraints, scheduling delays, and proprietary data policies which, while routine in scientific practice, have in this context become fertile ground for speculation about concealment. Despite these similarities, it's important to emphasize that the current situation with 3IATLAS does not entail an impending existential threat comparable to the fictional comet. The object's trajectory and physical characteristics strongly suggest harmless passage, and the scientific consensus remains that no impact is imminent. Nonetheless, the way information is handled and perceived, amplified by social media and headlines about near-miss asteroids and enigmatic interstellar visitors, often dominate news feeds, capturing public curiosity and generating vast engagement through sensationalism. Yet these headlines tend to obscure the nuanced scientific realities and the critical safety assessments that should underpin public understanding. Behind the dramatic narratives, genuine research aims to evaluate potential risks, but the media's focus on spectacle can distort this essential context, leading audiences to overlook the rigorous scientific processes involved. This phenomenon echoes a broader issue depicted vividly in the film Don't Look Up, which explores how legitimate scientific concerns are frequently misrepresented when filtered through political and economic interests. The movie illustrates how urgent issues, such as a threatening comet, can be marginalized or distorted when immediate benefits or short-term political gains are prioritized over long-term consequences. Similarly, the ongoing situation with 3IATLAS involves complex scientific questions that are being interpreted within frameworks shaped by a mixture of government secrecy, media sensationalism, and popular culture's conditioning about alien contact scenarios. One of the most prescient elements of Don't Look Up was its portrayal of how extraordinary events tend to become normalized through relentless exposure and saturation in the media landscape. Over time, the initial shock and intrigue surrounding the fictional comet diminish, relegating it to the background noise of celebrity scandals and political controversies. This process of normalization threatens to occur again with 3IATLAS, especially as the natural curiosity and excitement fade during the upcoming conjunction period, which will temporarily remove the comet from immediate visibility. The film's critique of the struggle between scientific authority and populist skepticism resonates strongly with the current circumstances. In Don't Look Up, astronomers find it difficult to maintain credibility amidst a media environment saturated with charismatic personalities and emotionally charged narratives that divert attention from scientific facts. The debate surrounding 3IATLAS mirrors this tension, where careful scientific methodology is challenged by more sensational interpretations that appeal to public imagination and fear. However, it is essential to recognize that Don't Look Up's satirical framework is not a call to dismiss legitimate questions about transparency and the sharing of information. Rather, the film highlights real issues in how institutions manage long-term complex challenges, issues that do not fit neatly into existing political or economic agendas. The current absence of high-resolution images from major space telescopes, coupled with the timing of the upcoming superior conjunction, when the comet will pass behind the Sun from Earth's perspective, creates natural gaps in data that are ripe for speculation. While operational constraints and safety protocols explain some delays, these patterns of information withholding bear a troubling resemblance to the media and government strategies depicted in the film. This situation also echoes broader societal attitudes of complacency and denial. Many people have grown numb to reports of asteroid approaches and comet discoveries, often dismissing them as routine or inconsequential. This normalization of space-related phenomena as mere entertainment reflects a deeper vulnerability, the human tendency to overlook or underestimate the significance of complex scientific data. Don't Look Up ultimately warns that humanity's greatest weakness lies not in external threats alone, but in our collective inability to process, understand, and respond effectively to challenges that extend beyond the typical timeframes of political and economic cycles. The 3IATLAS scenario tests these same vulnerabilities. While it does not pose an immediate existential threat, the risk that public interest will wane and that critical information might be suppressed or overlooked remains. The pattern of delayed or absent high-resolution data, the upcoming conjunction blackout, and the potential for misinformation create a perfect storm for the normalization and possible trivialization of these extraordinary phenomena. This underscores the importance of maintaining transparency, fostering public trust, and ensuring that scientific findings are communicated accurately. Lessons that Don't Look Up dramatizes with biting satire. The conclusion of the film, where a catastrophic comet impact unfolds despite advanced warning systems and our technological capacity to avert such a disaster, functions as a powerful allegory emphasizing the critical importance of preserving institutional credibility and fostering unwavering public trust in scientific expertise. This narrative serves as a stark reminder that even when we possess the knowledge and tools to prevent catastrophe, the effectiveness of our response hinges fundamentally on the integrity and transparency of the institutions responsible for managing crises. The situation with 3IATLAS presents a unique real-world opportunity to demonstrate that scientific and governmental systems can indeed operate effectively when faced with genuinely extraordinary and unprecedented phenomena. The key challenge for scientists, policymakers, and media outlets is to strike a delicate balance. Maintaining transparent and honest communication about the uncertainties and peculiarities of what is observed, while simultaneously avoiding the pitfalls of jumping to premature conclusions or resorting to excessive secrecy that might erode public confidence. The satirical scenario depicted in Don't Look Up vividly illustrates how quickly public trust can be compromised when institutions seem to prioritize political agendas or economic interests over candid communication and scientific integrity. As 3IATLAS continues its slow journey toward conjunction and eventual reappearance, the manner in which information about its unique characteristics is handled will serve as a real-world test, one that could reveal whether the dysfunctional dynamics critiqued in the film truly reflect inevitable human limitations, or are instead preventable failures rooted in poor leadership and flawed communication strategies. The overarching message of Don't Look Up underscores that confronting extraordinary challenges, be they climate crises, global pandemics, or potential first contact with extraterrestrial intelligence, requires unprecedented levels of cooperation, transparency, and mutual trust across all institutional boundaries. The stakes are simply too high for the petty political games and manipulative tactics that the film criticizes. While the film primarily explores the destructive potential of political and social dysfunction in the face of imminent disaster, the case of 3IATLAS raises a different but equally profound set of questions. It prompts us to consider how humanity might respond, not to an immediate existential threat, but to ambiguous, puzzling, and potentially revolutionary discoveries that challenge our understanding of life, intelligence, and our place within the cosmic order. These unusual characteristics, although not threatening in the immediate sense, might nonetheless herald paradigm-shifting shifts in scientific knowledge, advances that could be as transformative as the discovery of extraterrestrial life itself. In the next phase of this unfolding scenario, Part 14, titled Doomsday Speculations, we venture into pure thought experiments, exploring the outermost edges of what might be possible, rather than making predictions based on current evidence. While all signs indicate that 3IATLAS's unusual features do not suggest an imminent threat to Earth or a looming catastrophe, the human mind is naturally inclined to entertain the most dramatic and unsettling possibilities when faced with phenomena that defy familiar patterns. This cognitive tendency, born from the survival instinct of our ancestors who needed to anticipate potential dangers, now manifests as worst-case scenario thinking about interstellar visitors exhibiting unexpected behaviors. For example, what if the comet's nucleus were significantly larger than current estimates suggest? The Hubble Space Telescope's upper limit for the nucleus size is roughly 2 kilometers in radius. But if it were in fact much larger, it could contain vastly more volatile material, potentially explaining its rapid and unprecedented activity. Such speculative questions, while not grounded in current scientific consensus, serve to stretch the boundaries of our imagination and prepare us mentally for the unexpected. They highlight the importance of remaining open-minded and cautious in our interpretations, especially when faced with anomalies that challenge established models. As we continue to observe and analyze this enigmatic object, it remains vital to distinguish between scientifically grounded hypotheses and imaginative scenarios that probe the limits of possibility, enriching our understanding and readiness for whatever surprises the cosmos may hold. A radius of approximately 8 kilometers, coupled with ground-based survey data suggesting a diameter of just a few kilometers, currently stands as the most dependable estimate for the size of this interstellar visitor's nucleus. Yet it's crucial to recognize that these measurements hinge on certain assumptions, particularly about how reflective the surface is and the geometric configuration of the object, that might not hold true if the nucleus possesses exotic materials or an unusual internal structure. If indeed the nucleus were larger than estimated, it would logically contain a proportionally greater amount of volatile substances. This increased volatile inventory could potentially explain the rapid expansion of the comet's coma, as well as the atypical brightness fluctuations observed during its approach, phenomena that have puzzled astronomers and characterized its behavior throughout this close pass. However, proposing a larger nucleus runs counter to the most carefully calibrated and independently verified observational data. Such a discrepancy would imply that multiple measurement techniques, each with their own error margins, simultaneously produced systematic errors, a scenario that seems increasingly unlikely given the current level of observational precision. Another possibility to consider is that a fragmentation event might have occurred during the spacecraft's flyby near Mars, subtly altering the comet's dust output and brightness profile without immediately being obvious. It is well documented that comets, especially those with loosely bound nuclei, sometimes undergo splitting events triggered by tidal forces or intense thermal stresses. These events often lead to dramatic increases in brightness and an expansion of the coma, as fresh, volatile-rich surfaces become exposed to the sun's heat. Given the gravitational stresses involved in a close approach to Mars, such a fragmentation process would be physically plausible, and any resulting changes in the comet's appearance should, in principle, be detectable through light curve analysis and imaging data. Nevertheless, if the comet had experienced a significant fragmentation, it would also likely cause observable shifts in its orbit. Precise orbit determinations, derived from extensive astrometric observations over many months, would typically reveal such changes, especially if they were substantial enough to alter its expected trajectory. Any deviation from the predicted path would stand out against the high-precision measurements that now allow astronomers to forecast the position of objects like this comet with uncertainties measured in mere kilometers. What if instead the trajectory of this interstellar visitor underwent subtle modifications that current orbit calculations do not yet detect? Modern astrometry is remarkably precise, capable of predicting a comet's position many months in advance, with uncertainties so small they can be measured in kilometers. These predictions are based on thousands of position measurements accumulated over extended periods, making falsification or significant error in the orbital solutions highly improbable. To produce a meaningful change in trajectory, forces beyond the gravitational influence of known solar system bodies would be necessary. While outgassing from the comet's nucleus can generate small, non-gravitational accelerations, often in predictable patterns related to how the sun's heat affects the surface. These forces usually follow consistent and well-understood behaviors, such as the comet's rotation and solar heating cycles. Any deviation from these patterns might suggest either an unanticipated internal process or, in a science fiction scenario, the operation of artificial propulsion systems. This leads to a more speculative but intriguing idea that 3IATLAS could be actively releasing small reconnaissance probes or microsatellites, which then masquerade as natural meteoroids. Such a scenario belongs to the realm of science fiction, yet it raises fascinating questions about technological capabilities. Deploying payloads capable of surviving atmospheric entry, operating on Earth's surface, and maintaining communication with their parent spacecraft would be an extraordinarily complex logistical feat, requiring precise timing, advanced miniaturization, and robust engineering. If objects were ejected from the nucleus of 3IATLAS in this manner, their trajectories would likely be predictable, governed by the comet's orbital mechanics and the circumstances of deployment. These microprobes or fragments, following their own paths, would still be subject to the same gravitational influences as other small bodies and would follow trajectories consistent with the comet's motion, making their detection or distinction from natural meteoroids a formidable challenge. Nonetheless, if such objects were large enough or numerous, they could potentially be identified through detailed tracking and analysis, raising profound implications for our understanding of what constitutes natural versus artificial phenomena in the solar system. Throughout the vast network of meteor observation systems around the globe, patterns in fireball activity would likely stand out if unusual objects were regularly entering Earth's atmosphere. Such anomalies in meteoric impacts could serve as subtle signs of a larger, coordinated phenomenon, perhaps even a deliberate reconnaissance effort, rather than mere coincidence. During mid-September of 2025, a wave of asteroid encounters graced our skies, with several objects passing safely but with notable prominence. These objects caught the attention of both scientists and the public alike, traversing Earth's neighborhood and making headlines. Coincidentally, this same period coincided with the most peculiar behaviors exhibited by the interstellar object known as 3IATLAS. The timing raised an intriguing question. Could these asteroid passages be part of an orchestrated pattern, a form of covert data collection or reconnaissance rather than simple random events? In reality, close approaches of asteroids and meteoroids are a common occurrence throughout the year. Most of these encounters go largely unnoticed, producing minimal public interest unless they happen to align with media narratives or happen unexpectedly close to populated regions. The clustering observed in September, therefore, is more likely a reflection of our improved detection capabilities thanks to advances in sky survey technology and a heightened level of public awareness driven by the unusual activity of 3IATLAS, rather than an actual surge in asteroid activity. Furthermore, the heightened solar activity expected during the solar maximum of 2025 introduces additional factors that could influence interactions within our solar system. This period is characterized by increased solar phenomena such as coronal mass ejections and elevated levels of energetic particles. These events can produce spectacular effects in the behavior of comets, particularly in their ion tails. For instance, intense solar wind and magnetic disturbances can cause disconnection events, dramatic discharges where parts of a comet's tail break away, sometimes resulting in sudden surges in brightness or unusual geometric configurations that might appear anomalous to casual viewers. Such solar-comet interactions are well understood phenomena within the realm of space physics. They tend to become more frequent and intense during periods of high solar activity, but they do not pose any direct threat beyond the realm of routine space weather. effects that modern technology is specifically designed to withstand or mitigate. These events follow established scientific principles, and their occurrence is regularly monitored by space weather forecasting agencies. In the unlikely event that a genuinely hazardous object or event were detected in connection with 3IATLAS or any other solar system body, the global astronomical and space security infrastructure would activate established alert protocols. The Minor Planet Center, responsible for tracking near-Earth objects, works in tandem with the Jet Propulsion Laboratory's Center for Near-Earth Object Studies, which maintains continuous surveillance capabilities. These organizations coordinate to evaluate impact probabilities and potential threats, providing real-time assessments. Parallel systems operated by international agencies like the European Space Agency's Space Situational Awareness Program facilitate independent verification of trajectory calculations and threat evaluations. These networks ensure that any genuine danger would be swiftly identified and communicated through official channels, minimizing the risk of any threats remaining obscured or unnoticed by the public. Despite the dramatic narratives often associated with celestial threats, the objective probability of a catastrophic impact remains exceedingly low. Human cognition, however, tends to amplify fears through cognitive biases, particularly with phenomena that challenge current scientific understanding or involve objects originating from beyond our cosmic neighborhood. The allure of conspiracy theories and apocalyptic scenarios often exceeds their actual statistical likelihood, feeding fears that may be fueled by misinterpretation or sensationalism. In the case of the 3IATLAS situation, multiple lines of evidence, such as its trajectory maintaining safe distances from all planets, serve to constrain the scope of possible scenarios. The object's path and behavior align with natural celestial mechanics, and current models suggest no imminent risk of collision or catastrophic impact. While the phenomena surrounding it are indeed unusual, they fall within the spectrum of natural variability and known space physics. Thus, while the universe continues to surprise us with its complexity and occasional anomalies, our existing scientific infrastructure and understanding provide robust safeguards. They assure us that, despite the sensational narratives, genuine threats would be swiftly identified and addressed by the international community of space agencies and astronomers, ensuring that the safety of Earth remains a top priority amid the ongoing marvels of our cosmic environment. As the interstellar visitor known as 3IATLAS hurtles toward its anticipated rendezvous with the inner realms of our solar system this October, a striking array of distinctive features continues to set it apart from every other celestial object previously studied by astronomers. These characteristics seem almost deliberately designed to draw attention and challenge our current scientific understanding, creating a puzzle that compels caution yet invites profound opportunity. The first of these puzzling traits is the comet's sudden and unexpected brightening during mid-September, a rapid increase in luminosity that diverged sharply from the predicted light curves meticulously derived from decades of careful observation and well-established physical models. In the realm of cometary science, brightness models stand as some of the most reliable tools for prediction, built on a foundation of detailed data and a robust understanding of how ice sublimates under the influence of solar heat. These models have consistently held true for countless comets originating from our solar system's Kuiper belt or Oort cloud, where the physics of sublimation and dust scattering is well mapped. Yet when 3IATLAS's brightness suddenly surged above the expectations, violating the assumptions that have repeatedly proven accurate, the anomaly was impossible to ignore. It was neither subtle nor marginal. The deviation was pronounced enough that amateur astronomers around the world observed the comet shining more brightly than sky charts or prediction algorithms suggested it should. This unexpected brightening forced professional astronomers to revisit their models, recalculating and questioning whether they had overlooked some fundamental aspect of how interstellar objects, particularly ones from distant star systems, respond to solar heating. Such a deviation hints at underlying processes or compositions that do not conform neatly to our existing understanding, suggesting that the comet might be exhibiting behaviors influenced by exotic materials or internal dynamics altogether different from those of typical solar system comets. Adding to the enigma is the second major pillar of its peculiarity: the extraordinary expansion of its gaseous atmosphere, or coma, coupled with a chemical composition that defies conventional categorization. The coma surrounding 3IATLAS is dominated by carbon dioxide and stretches across hundreds of thousands of kilometers, an immense fuzzy envelope that challenges our notions of how a relatively small nucleus can sustain such prodigious outgassing. Spectroscopic data gathered by the James Webb Space Telescope has revealed chemical ratios within this coma that are unlike anything observed in our local comet population, hinting at a formation environment or evolutionary path that is profoundly different from familiar examples within our solar system. The sheer scale of the activity, the rapid expansion, the unusual chemical signature, raises significant questions about the nature of this object's internal structure and composition. In particular, the dominance of carbon dioxide in its atmosphere suggests that it originated in an environment far colder than those typically associated with solar system comets, or that it has undergone a chemical evolution process that set it apart. These clues are not just scientific curiosities, they point toward a broader understanding of planetary formation and chemical diversity in other star systems, broadening the horizon of our cosmic knowledge. As the comet continues its journey inward, these features, its unanticipated brightening and its massive, chemically peculiar coma, serve as both a challenge and an opportunity. They compel us to refine our models and expand our understanding of how objects from other star systems might behave when exposed to our sun's energy. Whether these anomalies are the result of exotic materials, unique formation environments, or entirely new physical processes, they underscore the profound significance of 3IATLAS as a natural laboratory for studying the diversity of cosmic phenomena. In the grander scheme, if further observations confirm that its behavior adheres to natural but previously unrecognized processes, then 3IATLAS will have greatly enriched our understanding of planetary formation, chemical evolution, and the dynamic environments of other star systems. Conversely, if evidence accumulates to suggest that its unusual characteristics point towards something more extraordinary, perhaps remnants of advanced extraterrestrial technology, the implications for humanity would be staggering. We could be on the cusp of discovering that intelligence and technological activity of galactic scale are not just theoretical possibilities but observable realities. Nevertheless, beyond these profound questions of origin and nature, there is an aspect of 3IATLAS's behavior that continues to captivate both scientists and the public in a manner that transcends purely rational analysis. Its uncanny appearance, rapid changes, and mysterious signatures evoke images of alien engineering and otherworldly intelligence, fueling fascination and speculation that stretch beyond empirical science into the realm of imagination. As the comet races toward its October rendezvous, the universe's most compelling enigma remains. Is this object merely a natural formation? Or does its bizarre and captivating behavior hint at something far more extraordinary? An alien presence silently observing from the depths of space? The unique chemical composition of 3IATLAS offers a compelling clue about its origins, suggesting that it formed under conditions vastly different from those that produce typical comets within our solar system. The unusually high concentration of carbon dioxide, combined with the rapid rate at which its surrounding atmosphere is expanding, points toward either an exotic mixture of volatile materials or sublimation processes that operate far more efficiently than our current models can account for objects situated at this distance from the Sun. Such an anomaly indicates that either the comet's internal makeup is fundamentally different, possibly containing substances or compounds unfamiliar to us, or that some unknown mechanism is energizing its sublimation, causing it to release gases and dust at a pace that defies established scientific expectations for objects at this orbital position. Adding to the intrigue are the extreme polarization measurements that have left experts searching for natural explanations, with no straightforward answers in sight. The minimum polarization value recorded, around -2.7% at a phase angle of roughly 7 degrees with an inversion point near 17 degrees, embodies a set of characteristics that no known natural object has ever displayed. Polarization data serve as a diagnostic tool far more revealing than brightness or spectral analysis alone. They provide insights into how dust grains scatter light, depending on their size, shape, composition, and surface texture. The fact that 3IATLAS's dust produces polarization signatures unlike any previously encountered material suggests two possibilities. Either it formed under highly exotic conditions or it consists of materials that do not exist within our familiar solar system inventory. These three unusual features, anomalous brightening, extraordinary atmospheric expansion, and unprecedented polarization properties, combine with the visual spectacle of a vivid green fluorescence and the peculiar anti-tail geometry to craft an appearance that seemingly hints at artificial origins. The comet's otherworldly look extends beyond mere superficial impressions. The precise physical measurements and behaviors defy straightforward scientific explanation, challenging our current understanding of cometary physics. Current orbital calculations reassure us that 3IATLAS will maintain a safe distance from Earth throughout its passage through the inner solar system. Its closest approach on December 19th at roughly 1.8 astronomical units ensures that, regardless of its true nature, it poses no immediate threat of collision or harm to our planet. Similarly, the encounter with Mars on October 3rd presents a valuable scientific opportunity rather than a danger. This upcoming flyby allows spacecraft equipped with advanced instruments to gather detailed data on the comet, transforming what might seem like a potential hazard into a rare chance for direct observation. The timeline leading up to the upcoming superior conjunction, when the comet will pass behind the Sun from Earth's perspective, sets the stage for a natural experiment in information accessibility and scientific transparency. As of September 22nd, no new high-resolution images from major space telescopes have been made publicly available, despite the comet's ongoing evolution and the intense interest of the scientific community in documenting its unusual properties. The Gemini South Observatory's striking image taken on August 27th remains the most detailed professional photograph accessible to the public, highlighting a stark contrast. Amateur astronomers and social media users continue to fill the digital space with spectacular images of the comet's increasingly dramatic appearance, while the calibrated high-resolution data typically provided during significant astronomical events remains conspicuously absent. This gap in detailed observational data feels especially noticeable given the comet's escalating visual spectacle throughout September, fueling curiosity and suspicion about what might be happening behind the scenes. As the celestial dance progresses into late October, a natural yet strategically significant event is set to unfold, the conjunction period. During this time, the interstellar visitor known as 3IATLAS will become effectively hidden from Earth-based observation platforms, coinciding precisely with its peak activity as it nears perihelion, the closest approach to the Sun. While this alignment can be explained through well-understood celestial mechanics, its timing opens the door for a range of interpretations. To skeptics and conspiracy theorists, it provides an ideal backdrop for speculation, suggesting possible concealment or deliberate suppression of information about this extraordinary object. For professional astronomers and space agencies, however, it presents tangible operational challenges, complicating efforts to monitor and document the comet during its most dynamic and revealing phase. Despite the observational blackout on Earth, the vast network of spacecraft orbiting within the solar system will continue to maintain their surveillance capabilities. Instruments aboard these spacecraft, positioned around Mars, Venus, and the Sun, are expected to gather crucial data that could shed light on the true nature of 3IATLAS. In particular, the impending flyby of Mars on October 3rd is seen as a potentially final opportunity to capture high-resolution images before the comet slips behind the Sun's glare. These observations are of paramount importance because they might provide the last best chance to understand the comet's internal structure, composition, and activity levels, before the conjunction obscures its visibility. The manner in which the scientific community manages and disseminates data about 3IATLAS during this critical period will set important precedents for how humanity approaches discoveries that could be revolutionary, whether they confirm natural origins or suggest something far more extraordinary. The current convergence of the comet's peculiar observational features combined with deliberate information gaps and its striking visual spectacle places existing scientific institutions under scrutiny. These circumstances test the credibility of the authorities and challenge public trust in the integrity of the scientific process. Whether 3IATLAS ultimately proves to be a naturally occurring phenomenon or an artifact of unknown origins, its presence has already left a profound mark on both astronomical research and collective consciousness. This enigmatic object has prompted scientists to revisit and question long-held assumptions about interstellar visitors. Observations of 3IATLAS have rapidly fueled widespread speculation about the possibility of alien intelligence and reconnaissance missions. Ideas that once belonged solely to the realm of science fiction but are now taken more seriously in light of its bizarre behavior. Despite the allure of these theories, the most honest and cautious assessment remains that natural explanations, although increasingly stretched, have yet to be definitively dismissed. The comet's extraordinary volatile chemistry, unusual internal structures, and formation conditions, distinct from those typical of objects within our solar system, could in principle account for the observed anomalies without invoking artificial origins. Nonetheless, the mounting evidence challenges our conventional understanding of what natural objects can look like and how they are expected to behave. 3IATLAS operates at the very edge of current scientific knowledge, exhibiting properties that might necessitate significant revisions to existing theories or the consideration of entirely new frameworks. Its peculiarities could either be the result of an unprecedented natural phenomenon, potentially the most unusual interstellar object ever detected, or they might signal the first direct evidence that advanced extraterrestrial intelligence has developed the capability to conduct reconnaissance across vast, light-year-scale distances. As this icy interloper continues its slow but relentless approach toward perihelion, each new observation holds the potential to tip the balance of understanding. The upcoming data, whether it confirms natural origins or hints at something more technologically advanced, could provide the definitive answers scientists have sought for decades. For now, the universe's most mysterious visitor remains a compelling puzzle, one that may soon redefine humanity's place in the cosmos. In the coming weeks, the world's scientific community will stand at a crossroads, determining whether 3IATLAS will be remembered as an extraordinary yet naturally occurring phenomenon that broadens our understanding of the universe, or as the definitive evidence that humanity is not alone, that advanced extraterrestrial civilizations are actively observing us from across the vast expanse of light years. As this enigmatic interstellar visitor draws nearer to the inner reaches of our solar system, its appearance grows increasingly uncanny, almost alien in nature. Whether this otherworldly look truly signifies origins beyond our planet, or simply reflects unfamiliar natural processes operating under conditions we've never before encountered. The question at the heart of modern astronomy remains profoundly compelling. When 3IATLAS finally emerges from the obscurity of superior conjunction in late November and into December, humanity will be afforded a rare opportunity, one that could redefine our place in the cosmos. We will learn whether this object is a vessel engaged in the universe's most advanced reconnaissance mission, silently gathering intelligence on distant worlds, or if it is merely a spectacular manifestation of exotic natural phenomena, a cosmic anomaly pushing the boundaries of our scientific knowledge. The implications of this discovery are monumental. They could either revolutionize our understanding of the fundamental laws of physics or serve as the first undeniable sign that intelligent life exists beyond Earth, actively observing and perhaps even influencing the galaxy. In either case, 3IATLAS will undoubtedly go down as one of the most significant objects ever observed in our skies, its true nature poised to reshape humanity's perception of the universe and our place within it.